Hello everybody, my name is Mathieu Andreu, I'm one of the organizers of this event. So welcome to this first Federated Learning and Privacy Preserving Machine Learning Workshop. We are really happy to have you today both on-site and online. So this is a hybrid event which follows two introductory events that took place over the last months. I'd like first to thank all the speakers who have agreed to join us today to give, I hope, wonderful talks on their research. I also would like to thank our organizers, our sponsors, and our host today, Sorbonne University and Sorbonne Center for AI, who have made this event possible. So please check, for those on site, you have received a flyer with all the information regarding the location of the coffee breaks, lunch, and the cocktail at the end. Please put your phone in silent mode. Also, please wear your mask when you're inside the auditorium. Nobody wants a cluster. We're really happy to be able to have an event on site after COVID. And also, please wear your badge at all times, as this is proof that you've been controlled for your health pass. I will now leave the floor to Gérard Biot, who is the director of the Center for AI, and who would like also to make a short note.
Thank you very much. Okay, so good morning, everyone. I'm going to make it 50% in French and 50% in English. So, la partie française, hein, donc Gérard Biot, je suis professeur à Sorbonne Université et directeur du centre IA, SKY. Donc SKY, hein, c'est un institut de Sorbonne Université qui a été créé en 2019 et qui a pour vocation d'animer la recherche et l'information dans le domaine de l'intelligence artificielle dans notre établissement et dans les établissements associés. Donc SKY agit de façon transdisciplinaire et transsectorielle. Transdisciplinaire, ça veut dire que nous essayons au maximum de faire en sorte que toutes les disciplines concernées par l'IA dialoguent. Et transsectoriel, ça signifie que nous essayons au maximum de travailler avec des partenaires du monde industriel. Donc c'est dire, hein, si la journée d'aujourd'hui rentre pleinement dans l'émission de Sky, et nous sommes vraiment ravis d'accueillir les orateurs de la journée en partenariat avec Hawking, Accenture et le groupe jeune, le groupe... Je vais vous expliquer pourquoi je dis le groupe jeune, mais le groupe Malia de la SFDS. Donc vous avez devant vous un directeur de centre heureux, mais donc qui est aussi heureux dans un titre plus personnel, puisque je suis ancien président donc, de la Société française de statistique, et qu'en mon temps, j'ai beaucoup œuvré pour que se crée le groupe Malia, le groupe d'apprentissage statistique et d'intelligence artificielle. Donc c'est pour ça que je parlais du groupe jeune, parce que beaucoup aujourd'hui d'acteurs du groupe Malia sont des anciens membres du groupe jeune de la SFDS. Donc voilà, donc je suis vraiment très très heureux de voir que tout ceci a pris son envol, que c'est, m'a-t-on dit, la 3e édition du partenariat avec Accenture et Hawking. Et donc la journée s'annonce magnifique. Hein. Je vous souhaite à toutes et à tous vraiment un beau colloque. Je vais rester autant que je pourrai parce que le sujet est vraiment passionnant. So maybe the English part. So just a few words to welcome you all, to wish you a very exciting day. I would like to thank, of course, the speakers who are going to be amazing today, and also the organizers. Of course, the organizers from Accenture, from Hawking, from the SFDS, and from Sky 2. So thank you all, and please stay until the end, because tonight you will have a lunch, it's an aperitif on the top floor of the Tour Zamansky, and the weather is beautiful, so please stay. I mean, it's worth enjoying it. Okay, have a very nice day, and see you later. Thank you.
Okay, so hi everyone. I'm Edouard Yallon. I'm one of the members of the SFDS, of the group Malia, and I'm going to introduce our first speaker. So our first speaker is Marco Lorenzi, who is a research scientist at Sophia Antipolis and Université Côte d'Azur, and his talk will be about federated learning for biomedical application from practice to theory.
Hello? Okay. Very very good, thank you. Good morning to everyone. But before to start, I really would like to thank the organizer of this event and for inviting me. And it's really great to be here. It's the first live meeting I'm having after a very long time, so it's particularly special today. And so I'm Marco Lorenzi. I'm a researcher at INRIA Sofia Antipolis in the EPION research group. And what I'm bringing today is somehow my experience as a researcher that is trained and has an experience in biomedical data analysis, and why actually federated learning is becoming so relevant for people like me. So we have been developing methods for analyzing complex data, biomedical data, medical images for many years, but in the past few years we have experienced a sort of revolution under different aspects. First, from the data aspect, data is becoming larger and larger, more heterogeneous. Models are becoming more and more complex and very data hungry. But on the other side, also in the last year, data is becoming more and more concerning, especially concerning the ethical aspect, access, privacy, and so on. Today there are very important regulations around what we can do with data, where we can store data, and so on. So this has dramatically changed the way we conduct research and actually brought important problems to our daily life, daily routine. And that's where actually federated learning is becoming, or is actually currently becoming, one of the main paradigms for a biomedical data analysis project. You can see it's a very quick research on PubMed, but how the word federated learning actually exploded in the publication in the past 4 years. And more and more people are interested into this, more and more groups around the world, because federated learning offers the opportunity of dealing with the centralized training of models. So we solve one of the critical aspects of the data, which is where data should be located. So we leave the hospital with their data, we can provide and guarantee that at least from that side, things are safe. And so the paradigm of federated learning is indeed, well, what I believe that many of us are already aware of, which is we can train local models, every center acts as a client, and then we aggregate parameters somehow. And this is done by a central entity, so we usually work in the star-shaped configuration. And then once a parameter aggregated, they are sent back to the clients that are using the parameters initialization for a new optimization round. And we iterate on and on. And there are guarantees that under certain assumption, with certain kind of model aggregation, things go well. So we converge somewhere, and somewhere is meaningful. So this paradigm, let's say the most, like the classical approach that implements this paradigm is called federated averaging, which was proposed a few years ago by McMahon and colleagues, so people coming from Google, in which basically the federated learning problem is formulated as a joint optimization. So we have different clients, each of them with their cost function, Fi. And we want to optimize the aggregation of the different cost function according to some weights, Pi, where the weights Pi are the relative importance of the clients. It could be, for example, how many data points the clients have. And the way to solve this problem iteratively basically is, well, requires to draw from the classical literature on distributed optimization. And it turns out that this can be solved by iteratively averaging actually the weights, so the parameters which are computed at each client side, and averaging respectively to their weights. And also in the original paper of McMahon, they are already proposing to not to use all the clients, but to sample only some of them to speed up things. And so it means that for the ones that we are not sampling, so that are not involved in the current optimization, we just actually carry the all the weights, so the global weight. So this scheme has been proved in several ways under several assumptions to work. And although there are guarantees that this converges and leads to like a local optimum, it has been shown already in the original paper and then so on in many other publications that there are important pitfalls. The pitfall, the main weakness of federated learning is heterogeneity. So already in the original paper, we can see that when they were increasing heterogeneity in the data distribution and so on, the convergence actually was much impacted, much slower. And heterogeneity can mean many things actually. It's a concept which is very broad because it can be heterogeneity of distribution of features across clients, of labels, or also conditional distribution. So given the same label, the feature might not look the same across clients. And this is very, very, very common. And I invite you to actually take a look at this very nice review from Kairos and colleagues, in which they describe very nicely actually all this kind of heterogeneity. And the other issue of federated averaging that is very slow, because it requires actually clients to compute things, and we have to wait actually that they are done with their job. And there was already this concept of sampling, only few of them, but the problem with sampling, in the way they propose it, that there is no guarantee that this sampling procedure brings actually to an unbiased solution. So it's solving actually the original problem of federated learning. And so how to deal with this? So this is one of the main aspects when a researcher works in federated averaging, in federated learning, is to guarantee that actually we are doing things properly and we are representing clients properly. In biomedical application, this is imperative because biases can dramatically affect the quality of a model, for example, predictive model of certain pathology. So we have been working on this aspect, starting from the seminal work of Lee et al., which is the work introducing FedProx, in which they introduced the concept of unbiased sampling. So basically, we assume that at every round, we can sample a subset of clients according to some distribution. So we have some new aggregation ways that come from the way we sample, so how many times we sample the client. Usually we sample with replacement. And we require that in expectation, this is actually, by definition, has to be equal to the original objective of the aggregation of federated averaging. And so what they propose in this paper is just to use a multinomial distribution. We can imagine our set of clients here, each of them with their relative weights, so which can be interpreted as a probability of a client to be sampled at a given iteration. And so we can pick them, basically sample them from our bucket of clients, and aggregate depending on how many times the client is being selected. And so these are stochastic weight, because now they depend on a random process. And they are unbiased, because by definition, we are sampling them with, in expectation, the proportion to their probability, so to their weight. But the problem is that now we have something that varies across iterations, so we introduce variance in the process. And this is something that has been observed and is a known aspect of, for example, procedure like FedProx with sampling, is that federated learning is affected by large variability. And this can impact actually the quality of the model, the speed of convergence, and so on. And also clients we don't have guaranteed that they are equally represented at a single round. We'll have only these properties in expectation. So the idea, can we improve actually, or can we work on this concept actually to find better way of representing features and clients during federated learning? And this is one of the work that we have been proposing, and is done by Jan Fraboni, which is here today, a student that works in collaboration with Accenture. And so the idea is to sample this time not according to the single probability of the client, but according to, in a way that actually we enhance to cluster clients according to similar characteristics, so to enhance the representativity of meaningful things. And so clustering things, you can imagine from a sampling perspective, it means defining a sort of distribution that gives high probability to clients which are similar to being picked at that given sampling procedure. So the idea is that instead of sampling m clients according to a given probability distribution, so the multinomial distribution, we can actually sample according to k or m different distributions, each of them prescribing a given cluster. So we still sample m clients, But each time we privilege, we favor clients which are compatible according to a given probability density function. So these times, instead of having a single set of probabilities to sample from, we have basically a matrix of selection probability for each of the M distribution, which are the rows. We have a probability of sampling a given client. So this cluster sampling as a problem, as mathematical problem, becomes formulating a proper sampling rule, so a sampling matrix that describes distribution and clients. And we want to give guarantees, so we want to study this object. And actually, there are two conditions we need to prescribe for this to be valid sampling scheme for federated learning, which means being unbiased. First, we want that the sum over the column has to be 1, which makes sense because these have to be probabilities, distribution. And, but what we want also is that sum over the row has to be equal to MPI. So number of clients times the relative probability. And with these two conditions to be satisfied, we can actually prove that this sampling scheme is unbiased. And what is interesting is that given this new way of sampling things according to different distribution, we can prove that we can bound the variance at the process at this time by the original variance of FedProx, so the MD, multinomial distribution one. And also, the probability of a client to be represented according to the law that we prescribe is bounded, again, is higher than the original probability of multinomial distribution. So basically, we have a scheme that potentially can give lower variance and increasing representativity of the clients across iterations. This makes sense because under the classical assumption of federated learning, sampling, so aggregating according to the sampling scheme can be shown actually to converge to a minima across iterations. So this is still compatible with the original federated averaging. And the problem is how to specify this set of conditions. And it is a very complicated problem. They cannot be really optimized, or the optimization with respect to some cost function is difficult. And so what we identified is actually some ideal or some rules that we can identify with respect to specific condition. For example, what happens if we want to cluster clients according to their sample size? So something which is similar to the original formulation of federated averaging. So we want to give more probability, more weight to clients which are more represented. So the scheme is here. This is an example just to illustrate the basic idea. For example, we have our 5 clients. We want to sample only 3 of them at each iteration. And we have 20 data points in total. And basically, and this is the sample size of each client. So the idea is to consider basically the problem of filling 3 buckets. So our 3 distribution with 20 elements, so the total number of data points that we have. And the idea is if we multiply this quantity by m, the number of clusters, we have basically these balls that we have to assign to all the buckets. And we can start from the clients with the largest number of data points, and we can start filling the buckets until we empty. And then we move to the next one, and so on, until we fill out the buckets. And this basically defines our probability distribution, in which the first probability will assign weight 1, so probability 1 to sample the client with the largest number of data points, and then we will have a different ratio. So clients are differently represented with different probability from each of these 3 buckets distributions. So we can do the numbers, we can verify that indeed, in this way, we verify actually the condition of our theorem. And so actually we can formalize actually this procedure and show that indeed it satisfies the proposition. So it's a valid sampling scheme. And the idea is that what can we build from this actually to find more interesting sampling schemes? And the idea is to cluster clients according to their similarity. So let's assume that the first round, clients are sending their weights. And we can aggregate weights together, so using some clustering technique actually, to find the partitions of our client space according to the similarity of their weights, for example, cosine similarity and so on. So we can define different groups of clients with their own numerosity, with their, that define a partitioning of the space according to some similar features. And then we can operate a scheme like fill in the buckets again according to now to these groups that we have defined in the very similar way that we showed before. And we can show that this can lead to a similar actually way of defining the sampling distribution, but this time the distribution, they favor clients which are similar, so they put similar clients in the same bucket where we are going to sample them. Again, we can formalize this, and we can show that if we sample this way, things are fine. It's still a valid cluster sampling scheme. And so it's going to be compatible with the federated averaging procedure. And here is an example of what this means. So this is a synthetic example. We took a NIST, we defined 100 clients, and we partitioned them. So each digit of a NIST is owned only by 10 clients. So it's represented in 10 clients only. So this is a highly heterogeneous setting because there is an important difference between groups of clients. And then we run, and we sampled 10 digits at every iteration. So ideally, what we would like to do is to every aggregation, we want just to sample the relevant clients. So we would like to sample only the clients which are representing different digits, so that we at every iteration, in the 10 clients we sample, we have the 10 digits represented. But if you imagine, like, if you sample these in ID or with just a multinomial distribution, well, this is not guaranteed. So we can have clients which are more represented, clients which are not represented. Also, this brings heterogeneity and brings this famous variance. And what we can see is that when we use cluster sampling, so the red based on client similarity, well, we can see that the convergence actually improves and the variability is much decreased, especially after a certain number of iteration, because it means that at this point, the cluster that the scheme is going to identify are becoming meaningful, so are indeed grouping clients which are similar. So if you compare with the target distribution, so the target scheme is the ideal, so when we sample indeed 10 clients, each of them providing a different digit. So what we would like to do in reality, we see that we are getting very, very close. And the exemplification of what's happening is here. So here we are just quantifying each iteration, how many classes we are representing, so how many clients with different digits are sampled. And we can see that with standard multinomial distribution, we very rarely, actually, we are sampling different distributions, so different clients, different digits at every round. While with the scheme that we propose, after the model starts becoming meaningful, clients actually are clustered correctly, and then we guarantee that we sample all the time meaningful, actually, representatives. And this so ends up in better convergence and lower variability. Similar scheme when we work on different data sets, when we generate synthetic partitioning according to, for example, Dirichlet distributions. So from very homogeneous to very heterogeneous. So the colors indicate features which are represented for each client. And we can see that when we increase the heterogeneity, with no heterogeneity, basically all the schemes are the same, and the convergence is very similar, but when we increase the heterogeneity, actually algorithm 2 here is the cluster sampling by client similarity, and we can see actually that, again, we improve the quality of the aggregation. And so this was already a first proposal, how to address heterogeneity from a sampling perspective, so from a statistical perspective. And the nice thing is that this scheme provides some nice theoretical guarantees for convergence, variability, representativity. And it doesn't require to change anything about the original federated averaging process. We just change the way we pick the clients. So it's compatible with any possible extension that has been proposed for federated averaging, any setup. And of course, we provide some ad hoc criteria that are compatible with our theory. There might be others that can adapt to different scenarios, so this is an open research. And of course, this in biomedical application, in our case, this is effective, especially when we have a large number of clients, which might not always be the case when we work with a few hospitals. So even in this case, the scenario of application in biomedical application is still has to be perhaps investigated. Or then still dealing with variability, back to something which is more akin to a modeling perspective. We propose actually generative models to describe the variability across clients. So this is work of Irene Balelli, which is a postdoc working in our group. So the big problem we have when we're dealing with biomedical data is, again, heterogeneity, but of a very specific kind. Many times, features are not even represented in different clients. It might happen that some hospital have some imaging modality, for example, brain imaging. Others, they have some clinical data. Others, they have both. But there is this large difference in how things are represented. Missingness is a big issue. And also, there can be specific biases. And again, in our star-shaped network, in our aggregation, dealing with this can become complicated with standard schemes. So what we propose, we can imagine actually a data generation process from a probabilistic perspective. So the idea is that let's imagine that the distribution of the models across different clients can be described by some sort of statistical law, some probability law. So we can sample a distribution of models that fits actually every client. So basically we have something which looks like an hyperprior from which we pick actually distribution of parameters. And this describes actually how the data is generated locally. And once we have this law, we can generate the data. And so this is what we observe. So this describes a generative model, a forward model. And as in classical Bayesian paradigm, what we want to do is, given the data, we want to infer all the rest. So we want to infer prior, model weights, and even the hyperprior in this case. And so we can define a Bayesian network for this, and we can actually start prescribing, actually assigning these objects for distribution for all our quantities. And basically what we can say is that at the server we have some processes, some hyperprior that generate the parameter for every center, okay, and then these parameters are used in a generative manner to generate the observation. Here we focus on a latent variable model in which we assume that every client has some latent distribution that then is transformed, for example, through a linear transformation to generate the data plus some noise. And the transformation, so how the latent describes the data distribution, is specific to the center, to the client. So this is, in this way, something which is very similar to what is the original Bayesian PCA model, in which actually we also include this coupling term, which is given by the proprietor of the server. And we want actually to infer everything from the data. And this can be actually optimized using expectation maximization, in which, again, we have this alternate optimization procedure, which is very similar to the one which is classical for federated learning, in which actually every client updates the representation of the latent space, so the latent distribution. And then we can optimize with respect to the model parameters, accounting for the priors this time. So we get a maxima a posteriori. So somehow the prior acts as a regularization and forces every center not to go too far actually to what is the global distribution. And once we have all the parameters for every client, which are actually estimated, we can send them back to the server, as we do in federated learning, classical, and we can actually update the hyperpriors, as we do with the aggregation in federated averaging. So all this scheme is basically a generalization of standard federated averaging with this regularization term. So in this term, in a sense, you can see it as an extension or a Bayesian formulation of what is, for example, FedProx. And this is some example on some medical imaging and clinical data of a cohort of patients affected by Alzheimer's disease. It's the ADNI cohort, in which actually we consider healthy individuals and people with dementia, and each of them, they had a different kind of features attached. So medical imaging, so MRI, FDG PET, FD45, these are all brain imaging modalities which are different, clinical scores. And we considered a non-ID representation in which we can actually, certain center have some diagnosis which is represented, other not, and missing views across the different centers. And what you can see here, for example, is the variability the model infers for the latter representation of the different client. So we can see actually how we get this representation of the distribution in the latent space of the clients according to their specificities. And also you can see that the model is able to, well, identify the distribution of the features at the client side, even accounting for certain clients like here that are missing, for example, the pink one. And since it's a generative model, we can even impute data for clients that had that modality missing. And here you can see actually the reconstruction of the features for a client that didn't have those features at the beginning. So you can use actually for create missing information at the client side, leveraging on the information of the other clients. And it can be shown, well, we showed in different experiments that, well, this imputation reconstruction method outperforms competitors and standard aggregation schemes like federated averaging. But the important thing is that this provides a quantification and sound quantification of the uncertainty and heterogeneity that we have across all the data distribution. So it's a different paradigm for aggregation and uncertainty estimation in federated learning. And in a way is a generalization of what the original FedProx, because this coupling term can be seen as a Gaussian prior, hyperprior on the parameters. And what we have is a more complex or more extensive way of specifying coupling terms for parameters. Of course, sharing this kind of generative models raises some privacy issue, because when we can generate things based on other clients' information, we need to ensure that we don't generate things which are too close or they disclose sensitive information. And so we are currently exploring the privacy guarantees of the schemes and also extending to a more complex model beyond linear. And then to conclude, I just would like to present, so my talk I entitled From Theory to Practice, because if it's true from research we're interested in modeling data and well, accounting for heterogeneity, then when it comes to working with the clinicians, with hospitals, well, we need some practical framework, so software that can be used in these applications. And well, there is a so it's this the software landscape around federated learning is very dynamic. There are many initiatives. This is not a complete list of frameworks which are currently proposed available, and each of them has pros and cons. Among the most like notable pitfalls is the problem of handling different kind of model of optimization schemes, being actually not specific to some optimization library or machine learning library, and scalability when we did different clients, accounting for different sampling schemes, different aggregation, and being secured as well. So each of these framework, they tick some of this requirement, but they miss some of the others. And it's already a couple of years that we are involved in the development of Biomed, which is a framework that is currently actively developed in the area for federated learning. It started as an NRF-funded project 2 years ago, but rapidly actually became more and more supported. So now we are enjoying support from Troisia, which is the Artificial Intelligence Institute here in France, and from the National Plan for Artificial Intelligence. And Accenture is currently supporting in the development this framework. So we have a dedicated development team which is currently working on this. And the idea is that to have something that can be readily and safely used for our application in healthcare. So the architecture is basically, well, is here represented. We have a researcher that can actually prescribe models, and then we have this sort of middle layer, which is a third party, which is a micro service for communication and messaging, which is based on MQTT messaging paradigm for sending requests, and Django for sending, so REST API for sending model parameters. And on the other side, we have the clients. So it means that the researcher never accesses the clients, but there is always this mid layer trusted, which also permits to having only outbound communication from clients to researcher through this mid layer, which is something very important when we have to deploy things in hospitals. And everything is Dockerized, so it's portable, and there is a dedicated VPN for the environment. And so in the node side, what we have this local VPN, and we have this interface for actually sharing data sets, which are shared under the paradigm of tags, so that the researcher can query on the other side. And on the researcher side, we work quite extensively on this general paradigm for formulating models. So it's a class based, so there is this abstraction in which we have to basically, if you imagine how you would specify a PyTorch model, we have the definition of the model that we have to specify. And then we have a data loader. So basically this could be done pretty much by copy and paste from original PyTorch models. And then once we define this, which we call a training plan, so the model and the data, we just have to import what we call an experiment, in which we need just to specify which tags have to be looked for in the network, and giving the arguments for the training and running the experiment, in which we have also the possibility of defining different aggregators or client selection strategies. And then everything is run, and federated learning is performed. Actually, currently we support PyTorch, and also we are porting scikit-learn some of scikit-learn model, which are actually deployable within this scheme. But this is very general. So here I show you, this is Santiago Silva, which is a PhD student that actually performed this experiment with international, so they are different partners from France, UK, and the US. They were sharing brain imaging data, so neurological application, different representation of, for example, so quite a high level of heterogeneity in the diagnosis, in the age, and so on. So we train a classical variational autoencoder. So what I'm showing here is that the distribution, so of the data, for example, at the site, our site, France 1. And we can see that the model discriminates actually between healthy and unhealthy people. So it means the model learns something which is meaningful in this federated learning experiment. And here you can see we measure just some statistic of the aggregations time. And you can see that the center in the US actually was the one taking the longest actually to train, which makes sense because we had network, different condition in the networks. And this was based on a preliminary version of the algorithm, so it was something that we published last year. We much improved now. So we are currently exploring the possibility and setting up the deployment for this application in neurology based on what we showed before, and also with our clinical partners here in France, notably Olivier Humbert, which is another Troisier chair at the Centre Antoine Calacassagne, which is an oncology hospital, and partner hospitals. And there is much to do, still, especially concerning the privacy and the security aspect, but there is much that can be already done with what we have here. So I invite you, if you are interested, to take a look at our page. It's currently work in progress. It will be much better by the end of the month. But for anything like contacts, information, and why not also contributing? We are very open. It's a completely open source project. So to conclude, the federated learning is actually very fascinating and a key domain for actually real-life application of machine learning in sensitive cases, especially healthcare, which is the one that concerns me. most. It's still we are in an evolving period. Paradigm standards, everything is changing quite rapidly. So it means that it really requires to catch up and stay always tuned, which is interesting, but it can be also challenging. And also federated learning in practice is really complex. Requires a huge amount of coordination and following regulation, interacting with personnel at a very different side, from dev to researcher to clinicians to technicians and so on. So it requires large organization for being actually effectively run. And yeah, so I would like to thank all the people that from area is currently working with me and which are behind the most, if not all, the results that I show you so far. And I thank you for your attention. Thank you.
Thank you. Is there any questions? Not online? Yeah, please raise your hand if you have any. Oh.
Thanks for the night talk. You mentioned at the beginning these different kinds of heterogeneity and different types of heterogeneity, right, that can occur in practical problems. Can you comment a bit maybe on which kinds you think the two contributions you presented are suitable to tackle, and maybe which ones are not?
Yeah. So the heterogeneity, when it comes to sampling, the heterogeneity we tackle is heterogeneity over the model parameter. So for example, the client sampling that I showed based on the model similarity. So it's based on the assumption that clients which have similar data distribution, they will have similar model. And so data distribution in this case means, for example, the kind of feature which are represented, or even the kind of label. So in the MNIST, we have a paradigm where we have the heterogeneity of labels, and so also heterogeneity of features. But this can apply also when we have some drift of the features. Simply same labels, different features, so the model will be different. And so this client sampling based on model parameter similarity will still apply. The second paradigm is more related to, since a generative model can deal with missing data, which is another kind of heterogeneity. And since actually we allow this variability of model parameters, can also account for different distribution of the data, for example, how the features are represented, because this will result just in larger variability that the server will see in the distribution, overall distribution of the models. So these are the kind of heterogeneity. We don't deal, for example, with heterogeneity in sample size, which actually affects all of this, but in a different manner.
Okay, thank you. So we're running a bit out of time. So I guess we can thank again the speaker.
Thank you very much.
So our next speaker is going to be Martin Yagi, who is an assistant, tenure track assistant professor at EPFL. And so his talk will be about federated and collaborative learning towards personalization and robustness. If you get the slides.
Okay, thank you very much to the organizers for organizing this very nice in-person and virtual workshop. It's a great pleasure. It's been a long time. So I'd like to talk about federated learning and some extensions towards collaborative training, in particular on robustness on one side, and then also maybe personalization in the second part of the talk. So I guess we are all already aware of the standard setting that we consider here, which is also very well known. So just to put the goal that we want to achieve, the goal is really our data is distributed and it should remain like that. And while we have this constraint, we want to train a model which would still allow us to be a good model on all the data combined, right? Without actually combining the data. So this is the classic setting of federated learning. And that's what we consider in the first part. And then in the second part, I will also want to go a little bit further towards decentralized, which is a more general setting, which kind of includes federated learning. And it's a bit more general in two aspects. So one aspect is just that if we would like to have the same scheme being possible without a central coordinator. So the user should be able to decide themselves who they want to collaborate with and with whom they exchange gradients or updates. So that's one aspect, so that the kind of decisions of participating is back to the user. And so the other aspect is like, what are we optimizing? So I just said before that we just want to train a model which fits all the data, one model which fits everyone. So that's what federated learning does. But in decentralized, you could also ask, okay, maybe not everyone has the same objective. Maybe not everyone wants to learn the same thing. So maybe every user wants to train a separate model for their own purpose. Maybe the users have slightly different tasks they're trying to learn. So that goes towards personalization. So there are these two aspects. One, the lack of a central coordinator, and second one, what is the objective? Is it one objective or is everyone having their own objective? I'll try to comment a bit on both. And so, but let's start with the federated setup on the left, which is more standard. And also we always address this one first because it's kind of easier and also has many open questions already. So let's see what we always try to do something on the left, and then we can see, can we also translate it to the more general setting on the right. All right, the tools we're going to use, of course, are very standard, so don't be scared with the formula. So we just say that Fi is the loss or the learning problem of the agent I, of the person I collaborating. And then we just here, it's the global setting. We want the average of everyone's loss to be small, so that's just a federated learning setup. Of course, we do gradient updates, so the device computes a gradient on their own data, sends it somewhere, maybe with compression or not, and then the server will update it. So nothing special here. I just want to say that this is the tools that we're going to use for our purposes. Okay, so the first challenge I'd like to address is the one of malicious agents which might be present if you do federated learning. And what do I mean by that? So it's not really a problem if you have a very small number of participants and really trust them. If you do federated learning with like 3 hospitals and you set them up in a VPN network where everything is secure and you trust them, then we are fine, right? We usually don't have malicious agents, except we might have maybe unstable agents which are not contributing in some rounds. There might be downtime of a server or so. So that's the things that can happen. But if you do the federated learning with more and more participants or in a cross-device setting, which means like maybe user-controlled devices and maybe larger numbers of them, then you can also really have a malicious agent. What does that mean? So here we really try to allow any kind of behavior of that agent. So we have absolutely no control of what that agent might do, and that agent might try to break the system, try to break the training for everybody by sending bad updates in any way and trying to trick us as a server to accept those. So can a few of these malicious clients break the training process? Let's try to make this a little bit more formal. So this is really, again, the standard setting in federated learning. Everyone sends their updates. So these are the G vectors for gradients. Everyone sends a gradient. It goes to the server. It gets averaged, and then that's our gradient step. So this is federated averaging, as we know very well. So when this aggregation function is just the average of everyone's message. So this is done, and then the model W, after the update, is sent back from the server to all the clients. Again, we have one model for everybody. This is just standard federated averaging. But now you can already imagine that what can go wrong? So of course the average is not a robust function. So if there is just one malicious client, by making their message, making their gradient arbitrary high, you can imagine that this will completely break the result. You make the average to be anything the malicious agent wants it to be. So average is not a robust function, which we also know from statistics, but we have to be a bit careful what we mean by robust here, because we want to do optimization. We want to minimize the training loss for everyone over several steps. So I'll get back to that. So the mean is not robust. The median is. So this is the first intuition we have. So why don't we just use median instead of the mean? So okay, one question comes up is so these gradients, they are not numbers, right? They have many entries, so we need something like a median of a vector. Can we do that? And yes, there are several notions of geometric median which are available and can be used and are actually can be directly applied here. So maybe the simplest one is the coordinate-wise median, which just means, yeah, as the name suggests, you just treat every feature, every coordinate separately. You take the median there, and now hopefully you have something robust, right? Maybe now the median is not affected. If you just look at one coordinate, the median is not affected by one malicious worker. So the setting we will have is that we can have more than one malicious worker, of course. So we assume that a fraction or percentage of all the workers is malicious. Maybe, I don't know, maybe 30% of the workers are malicious, and the others are the good workers. So that's the Byzantine robust training problem, and here are some of the aggregation rules, as we call them, that people use to address this. There are other rules. This has been a very rich upcoming research area to develop better aggregation rules for this setting to be more robust, right? When a larger and larger fraction of the clients behaves maliciously by sending arbitrary messages. There is a problem with this, that how to get really the conversions results, because most of the existing literature only studied the robustness of the rule itself at one step. So what they were studying is just that the rule, which means aggregating the gradients in one round, is the result of this aggregation, is that close to the thing it should be. The thing it should be is the average of the good workers, if you exclude the bad guys. So that's what you want to achieve. So if your aggregation rule returns some vector, which is close to the true average of the good guys or girls, then this is a good rule. Then this is what we call a robust aggregation rule. So now the problem is that this is not enough, because we are not only doing one step, we're doing many steps in the optimization, right? So we have this rule, to use this rule many times, and then what happened is that kind of a big problem came up that you can have problems over time when you apply these aggregation rules many times. So the problem was that the robustness of the aggregation rule, that it's close in one step, does not imply that the resulting optimization succeeds. And the reason for the failure of this aggregation rule so far was exactly this kind of time-coupled problem, that it works well in one step, that's fine. But then if you do it 1,000,000 steps for your training process, then very small changes could be happening in each step, which is the malicious actor will just have a very small shift, which it applies in every step. But over the 1,000 steps you do, it will drag you in a direction to bring the model anywhere it wants, right? This is the problem, and this was known as the little is enough attack. There are like two papers. One paper is called False Empires. The other paper is called Little is Enough, and it's really what it says. So little change by the Byzantine agent can be enough to derail the conversions for over the time. So we need a kind of a new notion, or more careful notion of what the Byzantine robustness could be, in order to be able to guarantee that the training will still succeed. So yes, and we also looked a bit into what can really go wrong, and then we also saw that actually this aggregation rules, you can see that they can fail in a much more general setting, when actually any rule which does not remember from the past, any such rule can be tricked by the adversary, because it doesn't remember from previous round who were the good guys, and then it might fail to recognize this. The problem here is also that we use stochastic gradient descent. So to give you a bit of an intuition why this is that even among the good agents, there is a lot of noise because of stochastic gradient descent. So what the adversaries here kind of do in this little is enough is that they use very, very small steps which are kind of hiding in the noise of the good agents, right? And those makes it impossible for you to detect if you just look at one step. But if you look, so now we have to make a defense, right? So if you look at the defense over time, then you can hopefully detect who are the good agents. So that's what we're going to do to fix the problem. But on the negative side, you can see that if the rule does not remember, then you can be tricked by the agents. So which very few of Byzantine agents are enough to fail the training. Okay, how to fix this? I already indicated, actually the fix is extremely simple. You just use momentum, which everyone uses momentum anyway in deep learning. But here we use it for a very different purpose. So here we use it to stabilize the estimate of that these good agents give us in order to recognize them more easily. So this is a local momentum or client momentum. So I is every agent, right? So on every agent, you have its own momentum vector. And we use a very strong momentum if you want to very, very much try to get away with, to reduce the variance, to make the noise disappear on that agent so that we have a stable estimate MI of what this good gradient should be. And then we just feed this momentum corrected vector into the aggregation rule. That's already sent to the server. Now you can ask, of course the Byzantine agents will not respect this, but that's fine. We don't mind. They can do anything they want. Anyway, this only requires that the good participants do use this momentum and then send it to the server, and we can use the same aggregation rules as we have used before. Now, again, the main idea is that now we have actually used the history, and now we can over time be more careful. We can see that the good agents are kind of more stable, and we can recognize from there, and we can recognize if they are good or not. And that's what the aggregation rule does. Most of these aggregation rules are, we saw a few examples, for example, the medium-based ones. You can also think of it as trying to detect if some of these gradient candidates you get are close to what you consider a good gradient. And who do you trust? You don't know any of the others if they are correct or not. But what you can actually trust is your own gradient. So that's also one very simple aggregation rule that we use. That how do we decide what do we keep? We just compare it to our own data's gradient, and if it's kind of close to that, then we accept those and average them, and the ones who are too far, we just throw them away. So that's just nothing else than gradient clipping, but relative to some vector that we trust. So if we do this, then we get a nice convergence theorem, and this is very standard, which is saying that, the training now converges. So this is the very standard result in stochastic gradient descent. If you just look at the main convergence rate, so T is the number of steps we do, And on the left, we have the gradient norm going down with the number of steps. Sigma is the noise of the good agents. So this is a standard convergence rate of stochastic gradient descent on non-convex objectives. But I mean, we're not showing that you go to the true optimum, right? We just show that you go to a flat point, that's all. And the nice thing is that you kind of get a help from your collaborators. So that's the very most important thing usually, that if you have n agents collaborating, then you also want to be n times faster. And that's what standard stochastic gradient descent has, but it's not so easy to actually maintain this improvement of number of workers when you have the Byzantine actors. So the Byzantine actors are a delta fraction of all of them. So that's how you can see you will get a slowdown the more Byzantine agents you have. Again, like delta is maybe 20% or so 0.2. And then, yeah, I explained all the quantities. Actually, I didn't give you the full definition of the robust aggregation rule, but there is also a constant there on what it means to be for the rule to be robust. In one step, so this theorem is false if you don't use momentum. But if you use the rule with momentum, then you have this theorem, which is just giving you training convergence. Okay, to show a bit that this is a real, also practical problem, we see that actually, yes, all aggregation rules, if you do not use momentum, are very much affected by this attacks, which is the little is enough attack. And the rule, if you use momentum, is actually going to be the brown line here, which will be reaching the accuracy, which is as good as if you don't have any attacks. So, but you need to use momentum. And the other rules are very, I mean, they drop to almost random if you attack them. So random accuracy. This is on MNIST, but also would behave similarly on CFAR or so. So that's the first paper I wanted to talk about, which is about the history aspect. To be honest, there's not the full story. So there is one aspect I didn't discuss here, is the aspect of heterogeneous data, which is very important in a realistic setting. And that's also something that we look at in the second paper, which is on archive. Having heterogeneous data is very realistic. Every client has their own data distribution. And there is a big problem here if you have this and then you do Byzantine robustness. And the problem is that it's kind of impossible to detect if a person is giving you Byzantine gradients or if they're just truly strange. So if they just have very strange data. So it's kind of impossible to distinguish these two things, right? So there's some other techniques we can use to, and maybe we need to have then a bit an assumption on how heterogeneous are the good agents, and then we can use techniques such as resampling to also allow a robustness to happen in the heterogeneous data case. So yes, I guess that's for the first part on Byzantine robustness. And if that's okay, I'd like to move on a bit to the second part where we go, so we forget about federated robustness and we're trying to look a bit into personalization or also decentralized learning when everyone has their own objective. So the setting here is, yeah, the main change is that we don't do federated anymore, that we just have one model for everyone that's on top. But now we want to have everyone minimizing their own objective, their own training data. Everyone trains their own model. So actually everyone will have a different model W in this setting. It's easiest to consider this when you look from the perspective of one agent alone, which we call the agent 0. And I mean, their goal is just to train well on their own data. And then the other agents might be available, but they have completely different tasks, different data sets, and maybe different objectives. So the question now is if for minimizing your F0, does it help you if you get additional gradients from the others? So even if the others might have different objective functions f, so it can be a bit annoying, right? If you have trying to minimize f0, but then your collaborator here has, I mean, maybe their objective is the opposite of yours. Maybe their objective is minus what you want. So then the gradients will not be useful. So, but it's kind of up to you to decide what they send you, and then to decide if you want to collaborate with them, which means that you accept the gradients and average them with you, or if you want to reject them, if you think that the gradients they're sending me are useless for me, which can be for various reasons, right? Maybe they have bad data, maybe they just have a different task they care about, maybe they are malicious. There's many reasons why you might not want to collaborate, but there's also reasons why you want to collaborate, because if you collaborate with n people, there is an opportunity to be n times faster, because if each of them gives you one gradient, you can be n times faster if they are helping you. So that's the setting we want to address here. And otherwise, we usually put no assumption on these f's, but we do have, later we will have a measure on how different the fi's are from each other to describe how much they help our objective f0. So the way we were first looking at this was through this simplified setting of just mean estimation, which is not really optimization, but just trying to find the mean of everyone's distribution. So the problem here is really every agent has one probability distribution sampling from it, but then you can also get samples from your collaborators. But the problem is they have a different probability distribution than you, so they have a different mean and a different variance. So getting their samples, does that help you to more quickly converge to your mean if you want to, if that's your task to estimate the mean of your ONS distribution. And actually this, people in statistics have already looked at this before. This is very similar to what's called the James Stein estimator. And what you're actually doing is you're just kind of trading off the variance against the bias, right? Because the stuff you get from your collaborators is very biased, right? Their mean is very different from yours, so it might be far away. But it's still a reasonable idea to use their values because they will help you to reduce your variance. So, I mean, your samples are very noisy. So the more samples is always better, right? Even if they have a bit of a bias. So that's the idea here. And how you do it is you just use a very small weight alpha, which you then give to them. When you receive their samples, you average them with yours, but with a very small weight alpha. So now I already switched gears to the more general setting of optimization. So can we do a similar thing in optimization? And what we do here is the same thing. So you want to optimize your F0, you have one gradient from your F0, and then you also get gradients from everyone else, which is the gradient of Fi's. The question for you is how to use them. So do you want to trust them, give them a big alpha, or do you want to trust them very little, so give them a very small alpha? And your goal is just to improve the convergence of your optimization on the objective F0. So the answer is yes, they can help, but yes, we do need very small alpha. So in this case, in the first case here, we actually need alpha to go to 0 very quickly. So we cannot trust them too much, but as we converge, their bias becomes too big, so we cannot trust them anymore. But at the beginning, they do help us to reduce our variance. So then there is a small extension you can do, which is very nice. So you can try to actually estimate the bias that they have from you, right? So at the beginning, you know nothing on what their task is, right? If you knew, you could kind of try to compensate for it. You could compensate from the difference, for the difference of your task. You want to do F0, they are doing F1 or Fi. If you would know this difference, you could compensate for it. but we don't know it, so we kind of have to learn on the fly on what they are optimizing, and to then try to compensate for it by learning a vector C, which describes the difference of their model to our model. So that's what we're trying to do here. And this idea of trying to learn a difference of gradients between two objectives is also used in variance reduction algorithms like SVRG, and also in Scaffold, which is a federated learning algorithm, which tries to do the same kind of trick to avoid client drift, which is kind of the same thing as happening here, that one client might drift to F0 and the other client might drift to F1, so you have to compensate for it. And then we see that we can use a bit larger alphas if we do this. So this is really work in progress, we just started, but we're trying to prove that the convergence of this scheme is still benefiting from having more agents. We're trying to show that you have faster convergence, the more agents N are going to help you. And the measure we need for this to happen is actually a similarity of everyone's F to your F0. The notion of similarity is I guess, a big topic, which might be more discussion needed. So what we use is a bounded Hessian similarity, that the Hessians of everyone's objective is not too far from each other, which might be reasonable if you have smoothness, but it's not, maybe it's not the final answer yet. So, but this can give you a faster convergence if you have collaborators. Okay, and yeah, then how to set the alphas in practice is also a bit of an open question. So this, yeah, they are small, the alphas, but then also maybe in practically you could set them a bit more efficiently, more aggressively, which means larger alphas. And that's also why I tried to present these two topics in this talk together, because it's all about this decision of who do you want to collaborate with. That was already the case in the robustness, right? We said a robust rule is kind of doing the same thing. A robust rule is selecting, do I want to trust this agent Fi to help me as a server in the case, but can be here as well. So does it help me? And I need to do this maybe because of gradient similarity. That's why the robust rules look like, looking at these gradients, making a robust average of them, or looking how they are different from our true gradient. So it's about gradient similarity. And that's also here when you see, how do I set my alpha? If I have good gradient similarity, hopefully I can use a larger alpha. So that's how the two topics are a bit connected. Okay, I'm wrapping up, and similarly as in the first talk, I want to wrap up with something more practical. So all this theory is nice, but we also hope that we can actually play around with this. And what we see is many of the libraries for federated learning on the software side are often only simulations, like TensorFlow Federated does not allow you to really deploy it, I think, so far. So we would really like something which we can deploy on mobile phones or in the browser, and that's why we try to do something with JavaScript, which is quite, I mean, strange. JavaScript doesn't sound really like a scientific language, but it's getting very nice. I mean, it's getting more and more supported, and actually in modern browsers or phones, there is already very good support for machine learning things and deep learning, and there we just use a TensorFlow Federated, and then on top of it, you basically just write a small website to get these gradients, and then those get sent to each other or get sent to the server in the federated case. So this is a lot of fun to play around, and the code is really simple, and you can also, it's also kind of nice for students that they can play with it, add new applications. So far we have some applications for tabular data, but also image data. For example, we're trying to apply it for ultrasound images or other kinds of image data. It's rather easy to plug in new models and then see if those can be federated. And you can also play with it, just open a lot of browser tabs to simulate all these agents, and it works on real phones and in browsers. But yeah, there is a lot of more work to do, and hope to get some interest. If you want to collaborate with us, that'd be great. Send us send us your gradients, and we hope to aggregate and get a speed up. And there's many things to be done. For example, also to add robustness, which we don't have yet, right? This is just federated averaging for now, but in the decentralized case. There's some very important to add security, privacy, where we think to just use some simple secure multi-party computation like a secure aggregation to mask the gradients, to make the gradients private, but the model is public. So that's this JavaScript library, and that finishes my part. I have a few pointers if you're interested on the papers mentioned. Thanks a lot.
Thank you, Arsis. Very nice talk. Are there any questions?
Yeah, thank you. It's a very, very interesting talk. And so it's something that you already mentioned in your talk, which is the need of tuning these parameters, for example, the alpha, so all this regularization. And what is your, can you elaborate on how this in practice can be done when actually, yeah, we need to coordinate among different partners. So usually this should be cross-validated, but cross-validating things in federated learning can be complicated for many, many reasons. So how would you see this aspect?
Yeah, how to set good collaboration weights alpha. So in the robust case, when you do federated learning, we set the collaboration weights are a bit easier to set. Basically, we set them by, for example, gradient similarity on the server, right? So those gradients which are close, you keep them. The other you throw away. So in the federated setting, it's quite easy to do it practically. It will just amount to gradient clipping compared to a value you trust. So that's the aggregation weights I'm saying would be 0 or 1, right, for this case of robustness in federated. And then for collaborative, it's harder, I agree. It's pretty much an open question. So the weights we have here are very theoretical, right? They are small, and they are, for now, they are made such the convergence rate works. But I don't know how to, in practice, set them larger, maybe again by gradient similarity estimates, to make this faster in practice. So this we haven't done yet, but it's a great question. Thanks.
We have some time for a couple of questions. Is there someone? Yeah.
Thank you, Martin. So one question is on, once you're looking into sort of bias correction, so the bias could come from either the difference in what the individual nodes are trying to predict. As you said, they might be trying to predict something that is completely opposite to what you're trying to do. And that's the other source of bias could be kind of data that they have. Again, what is it, how different the data distributions are. So once you're looking into bias correction, are these two, or there could be, multiple other aspects. So are you sort of combining these two together once you calculate alpha, or would you be dealing with these two differently?
Thanks. That's a great question where the bias is coming from, and we saw it in the previous talk that bias can have many origins, and I also tried to mention a bit that it can be very hard to distinguish if in the heterogeneous case if data is malicious or data is just strange, right? So that's also one aspect of this bias. So here we kind of ignore this aspect in the theory because we say that whatever is the reason for the bias, we just try to learn it and correct for it. But you're right, in practice, if you have additional information where the bias comes from, then maybe it could be exploited to speed up the practical conversions. That would be interesting. Thanks.
We have some time for a last question. Maybe online. So let's thank the speaker again.
Thank you very much.
So we have now like a coffee break. The next session will start in 20 minutes. And secondly, like for the people who didn't get to the register desk, like could you go now and go for the checking? It would be very kind. Thank you.
Can you hear me? Yes. Okay, so we are going to restart. The next session, we are going to have two talks, one by Aurélien Belay and one by Laurent Massoulier, so two researchers. First, Aurélien, he's a researcher at INRIA in Lille. He's an expert on privacy-preserving machine learning. He is also an expert on federated learning and has been organizing several workshops on differential privacy, on privacy-preserving machine learning, and on federated learning. And he's going to talk about all those topics.
Thanks a lot. Hello, everyone. It's a pleasure to be here. Like the previous speakers, very happy to be in a scientific event in person. Thank you for the invitation. So I'm a researcher at INRIA in Lille, and today I'm going to be talking about privacy in federated learning. So maybe this can come to some people as a surprise. Okay, maybe we can believe that because we do federated learning, we are not sharing the data. So even if this data is sensitive, okay, there is no problem. But in fact, we know that this is not the case, and we even know that in a centralized setting where we only make public a model that it was trained on some data, in many cases we can attack this model to recover information about the data on which it was trained. So for instance, there are things such as membership inference attacks, where given the trained model, you are trying to infer the presence of an individual in the training set, which can be, of course, a privacy problem if this database contains, let's say, people with a specific disease, for instance. And you can do that, for instance, by exploiting the confidence that the model has about the data and the fact that in practice it will have bigger confidence for data that it has seen in training. You can go even beyond that, and in some cases you can make reconstruction attacks where in this case, you're even reconstructing some of the points that were in the training set. And so I've worked recently in the context of genome association studies where in some cases you can actually recover people's genomes in the data set, which of course is quite a big concern. And so all of this is already present when you only have access to the final model that was trained. And then in federated learning, you can argue in a way that this can get worse because it offers an additional attack surface. As we have seen in the previous talks, the server or the participants in federated learning, they will not only observe the final model, but they will observe model updates, a sequence of model updates from different clients, okay? And so, in fact, there has been some attacks that have been designed specifically for federated learning. I've provided a couple of pointers which show that things can get worse, okay? So we need to solve this. We need to do something more in order to get rigorous privacy guarantees. And so this is going to be the topic of the talk. We're going to rely on a mathematical notion of privacy to prove such rigorous guarantees. So this is known as differential privacy. I thought that probably not all of you are familiar with differential privacy, so I will try to provide kind of the basics of differential privacy. And then we will go into how to apply differential privacy in federated learning. First, in the case where you have a server, but that is not trusted by the clients. And so you want to have privacy guarantees with respect to the server. And then I will go to the fully decentralized setting, which is the setting that setting that Martin talked about in the second part of his talk, and show that in some fully decentralized contexts, we can in fact leverage the fact that there is no server to improve the privacy guarantees, provably. Okay? And then I will wrap up. Okay. Good. So let's start with differential privacy. So it's not very easy at first sight how to define what it means for an algorithm to be private. And this notion of differential privacy is now kind of the standard notion in many fields, including machine learning. So to try to understand a bit what it means, let's think about algorithms, okay? So in the context of machine learning or data analysis, an algorithm is something that takes as input some data, okay, x1 to xn, and outputs something, which could be, let's say, the parameters of the model trained on that data. In differential privacy, you reason about algorithms that are randomized, okay? So essentially their output is a random variable. There is a distribution over the space of outputs, and essentially the algorithm is sort of sampling from that distribution to materialize the output. And then what it means to be differentially private is, to illustrate that, you can think about an alternative world in the red world where the same algorithm is given the same data, except that one of the data point was changed. The blue point became the red point, which of course means that you will get a different distributions of output. And essentially differential privacy requires that the distributions are close in both cases and for all such data sets that differ in only one point. Okay, and close typically will be something that resembles the fact that for any possible output, the probability of getting that output in one case is close to the probability to have the same output in the second case. So a little bit more formally, it looks like this. A randomized algorithm A is epsilon delta differentially private if for all such neighboring data sets that differ in only one point, and all possible sets of output, we have this inequality, okay? The probability of having the output in this set when the data set was D is roughly the same as the probability of having an output that is in this set when the data set was D prime. And how close is quantified by those two parameters, right? So epsilon bounds roughly this ratio between the two probabilities, and delta gives you some kind of additional slack. And so just to fix IDs, to get kind of meaningful privacy guarantees, typically epsilon should be around 1, and not too much bigger than 1, and delta should be much smaller than 1 over n. Those are kind of rule of thumbs, okay? So there is a key principle here that I want to emphasize, is that privacy in this kind of definition is a property of the analysis, property of the algorithm, not a property of a particular output of an algorithm. And this is in contrast to previous notions that had been considered, things like k-anonymity, which define privacy as a property of the output, and we know that these things are essentially broken, so in many contexts, they do not provide any kind of robust guarantees. Like I said, this has become very popular now. The authors won the Gödel Prize for this in 2017. There's been deployments, like the US Census is since last year using differential privacy for their release, and so on, okay? So why is it so popular? It has, in fact, many interesting properties that I'm gonna summarize very quickly here in an informal manner. The first one is invariance to post-processing, which means that if you have a differentially private algorithm, then you can apply any function to its output, and essentially this will remain differentially private in exactly the same way. There is nothing you can do by looking or manipulating the output to make it less private. DP is robust to arbitrary auxiliary knowledge, which is super important. It means that even if the adversary has a lot of knowledge to start with, maybe it knows everything in the data set except one record that it's trying to attack, differential privacy is essentially, the guarantee is still just as strong because it bounds essentially the gain that the attacker gets by observing the output. Okay, so if the attacker knew a lot to start with, then he still knows a lot plus a little something, but not much more. And then finally, which is very important to design algorithms, DP is robust under composition, which means that if you apply different algorithms to the same data, and they are all differentially private, then the combined output of all these things remain differentially private. You will suffer a degradation in the parameter, which makes sense, because the more you compute or you reveal about a data set, the less private things will be, but the important thing is that you can keep track of this degradation and bound it, okay? Right, so this was the definition. So of course now, this nice definition, but we would like to design algorithms that satisfy this definition. So how can we do it? Well, one simple way is to essentially add Gaussian noise to the output of whatever you wanted to compute in the first place, okay? So if you think about the function f that takes as input a data set, it can be deterministic, and it returns a vector, which could be the parameters of a model trained on the data. The Gaussian mechanism works like this, so it needs to know or to bound the so-called sensitivity of the function, which is described like this. So essentially, it's the maximum change that the value of the function can get on two neighboring data sets. So when you replace one point by another, and then essentially you draw Gaussian noise, which is calibrated to the sensitivity and the privacy parameters that you want, and you release the true answer plus this Gaussian noise. Okay, and you can show that this satisfies epsilon delta differential privacy for any function. And you can see here, very importantly, that this induces a privacy utility trade-off, right? Because this doesn't come for free. The more privacy you want, the more noise you need to add, which means you will have more variance in your result, for instance, okay? In this case, the output is still an unbiased estimate of f of d, but it has more variance. Okay, so this is the price to pay, and this is unavoidable, at least as far as differential privacy go. One last thing, which is going to be very important for this talk, is that you can consider different trust models when you think about differential privacy. The very common one is the so-called central model or trusted curator model, which is the case where there is a trusted party that gets the raw data and then computes something on it, like trains a model, for instance, and then publishes the result, okay? So this is the most favorable model for differential privacy because you only only the final output gets revealed, right? Unfortunately, in practice, it's not so clear who this trusted party may be, okay, that any individual or any organization providing data trusts enough to give the data in the clear. So less and less people are thinking that Google, for instance, should be trusted in this regard, for instance. And so there's more and more attention now towards the more local model of differential privacy, where you don't assume that there is a trusted curator. There is possibly some kind of curator, but you don't trust it. And so that means you need to essentially randomize your contributions ahead of giving them to the untrusted curator, okay? And so in this case, you want privacy with respect to each individual record or each individual data set that participants contribute. And we will see in a second, of course, this second model is more costly in terms of cost of utility. You will need to pay more for privacy in the second model than in the first one. All right, so how can we try to apply this to federated learning? Let's think about first the case where we have a server. Again, this server is untrusted now. Let me introduce a few notations. So we're going to consider a set of K parties. Sometimes I will call them users or clients. Each party holds a dataset GK. I'll denote by D the union of all local datasets. Of course, this is federated learning, so this will never be materialized, right? We will keep these datasets decentralized. And then we're going to focus on, like in previous talks, mostly this empirical risk minimization kind of formulation, where we have a family of models parameterized by parameters, theta, and we want to solve problems of the form of minimizing, finding the parameters of the model that minimize an average objective function, the average of the objective functions of the clients, okay, where each fk is the objective of client k that depends only on its own data, okay? So we know that this covers a broad class of ML problems, and so we will focus on this formulation of federated learning. Now, if you have listened to the previous talk, you might have noticed some kind of high-level structure in most of the federated learning algorithms that use a server. And the structure is this, right? There is a bunch of rounds, and then at each round, each participant will compute a local model update by essentially computing something that depends on its data. And then we'll share this update with the server. And then the server will essentially get these updates and compute the average, aggregate these models, okay, in order to produce a new global model that is then sent back to the clients. All right, so in fact, this is very useful for us because designing a differentially private federated learning algorithm maybe at first sight seems kind of challenging. But now if you look at the structure, this aggregation part is the only place where there is some exchange of information, really, that depends on the data, right? So essentially, if you can make this aggregation step differentially private, then you can use the composition property of differential privacy that I introduced before to keep track of the fact that you do that several times over several rounds. And that gives you directly a differentially private federated learning algorithm, okay? So we have reduced the problem of differentially private FL to the problem of designing differentially private aggregation protocols. All right, so what is this differentially private aggregation? Just to make it as simple as possible, okay, let's think about things in one dimension, in a bounded space. Every party has a private value, theta k, let's say it is in 0, 1, and we want to accurately estimate the average of these values under a differential privacy constraint. Okay, so we're gonna now kind of focus on this subproblem because we know that if we solve it, then we can construct a federated learning algorithm with it. So how can we do that? So first of all, let's think about the central model. Not very relevant for federated learning, but let's think about what we could do there. Then you would have a trusted server that would get the raw private values, compute the average, and add noise to that, depending on the sensitivity of the average, okay? Easy. Now, we cannot do that because we don't trust the server. So if you think about now the local model, it means that each participant needs to add noise to its own value before sharing it with the server. Okay, and if you were to compute the sensitivities in both cases, you realize that the amount of noise that you will have in the final average in both cases is not the same, and it's much bigger in the local case, okay? For a fixed DP guarantee, the error is essentially of the order square root of k, larger in the local model, where k is the number of participants. Okay, and this is unavoidable, in fact. There are lower bounds for this. All right, so there is a problem, in a way, because we would like to, this will mean a large cost in utility, right? It means the variance of the average would be much larger in federated learning, and so this will, of course, have an impact on the final model and its accuracy. There are different ways to avoid this by essentially relaxing this local model. One way is to use cryptographic primitives, things like secure aggregation, secure shuffling, that can be used to close this gap. So there is quite some work recently on that. Okay, the practical implementation of these things is not always so clear, especially when k is very large, number of participants is very large, where you can have maybe malicious participants and so on. Okay, and so what I'm going to present here is a first contribution of a much simpler protocol that doesn't rely on any complicated secure computation or crypto, but only needs to assume that pairs of users are able to exchange securely. So they can exchange encrypted message that the server will not be able to read, but the server might be used as a relay, okay, to pass around encrypted messages. And so for this, you only need secure channels. And so this is typically, for example, you can implement this by setting up a public key infrastructure, right? So that clients can use a public key of another client to encrypt the message, and then only that client will be able to decrypt it. So this remains very, very simple, and I'm just going to abstract away this thing and assume that pairs of users can communicate securely without the server being able to read. And using this, we're going to allow users to talk to each other. Okay, so this is clearly a relaxation of the local model, because the local model is only based on adding noise locally. Okay, there is no interaction that is possible. So we hope that by this relaxation, we can do better in terms of privacy utility trade-off than in the local model. And here's the algorithm. So the algorithm is very simple. It relies also only on addition of Gaussian noise, but now you have two types of Gaussian noise. First of all, there are some sets of parties that will exchange Gaussian noise that is correlated. So essentially, two users K and L will talk to each other. They will generate some Gaussian noise, but one will add it and one will subtract it. Okay, so they will essentially sum to 0 if we add them together. And then each party draws some independent noise, some noise that is only known to that party. And then what is the value that is shared at the end of the protocol is this theta hat k, which is the sum of the private value, the sum of all the pairwise terms, noise terms that it has exchanged with others, and its independent noise, okay? So what happens if you do that? Well, you can now average these theta k hat, and what you get is an unbiased estimate of the average. This is easy to see, and this is easy to see also that all the green terms, all the big delta terms, they will cancel out, right? Because they sum to 0 in a pairwise way. And so you remain only with the variance that depends on the independent noise, okay? And essentially the intuition here is that these pairwise terms, they will help you hide individual values without harming the final utility, because they will eventually cancel out, okay? And this is the intuitive idea, and proving that this intuition is correct is kind of challenging. So here's what we got. First of all, let me clarify a bit the adversary that we consider. We consider a strong adversary, which is the coalition of the server with a proportion of malicious parties. Okay, so we assume that a proportion of users in the network collaborate with the server by sharing the information that they have received, for instance, the pairwise noise that they have exchanged with some other users. Okay, so that's quite a strong adversary. And here's the result that we can prove. So in this case, in this result, we do something scalable by letting each party randomly choose roughly log k other users in the system, okay, to exchange this pairwise noise. So this is very important for scalability, of course, because you only need to talk to a logarithmic number of parties. And so the number of messages and interactions remain small. Now you can set the independent noise to be exactly the same as you would do if you were in the central model. And there is some pairwise noise that you need to set. It needs to be large enough, roughly of this order. Then you can show that the algorithm satisfies epsilon delta differential privacy with delta of the same order as the central model. So there is a slight degradation in the delta, but this thing is small, and so the impact is very small. Okay, so in a way, we get trusted creator utility with a very simple protocol and only logarithmic number of messages per party, which means that this remains very efficient. All right, so in this paper, we also do correctness guarantees. So kind of going further with these malicious users, you can now assume that maybe these users will lie about their value, or maybe they will lie about the noise that they have drawn because they want to bias the result. So we also show that by using some cryptographic primitives on top of our protocol, we can even guarantee that force essentially the users to behave correctly or detect if someone has cheated. Okay, so this, so I won't talk about that, but you can check the paper. This is just an empirical illustration of what we can get. So to the left, this is essentially the variance of the estimated average. At the top, you get the local model, so you get very large variance. At the bottom, you get the central model for computing the average, and you get low variance. With our approach, the blue curve, we are very close to the central model, and of course, how close we are depends on the proportion of honest users, and the users are not malicious in the network. But in any case, we can sustain quite a nice proportion. And of course, this propagates to federated learning. So when you use this to aggregate models in federated learning, because of that, okay, you immediately see that the accuracy of the final model that you learn is very close to that of a trusted server, trusted creator model, while in the local DP case, you get essentially completely rubbish model. Okay? Good, so that was for the case of federated learning with a server. Now, what if we want to do more fully decentralized systems? Again, like Martin has introduced at the end of his talk, so we want to remove the server and let the parties exchange in a peer-to-peer manner. In this case, we're going to do something a little bit different. We're going to be a little bit wondering whether maybe this fully decentralized setting can naturally bring us a boost or an amplification of the privacy guarantees. And intuitively, one reason is that in a fully decentralized setting, you don't have anymore a server that observes all the messages, but you only have users, participating users, that have a limited view of the system. They only see the messages that they send and receive, right? And so the question is, okay, can this limited view be used to prove stronger privacy guarantees, essentially without changing necessarily the algorithms, just by exploiting this restricted view that the participants have? All right, so to do that, we need to define some kind of a variant of differential privacy to capture this limited view aspect. So first of all, just kind of a detail, but we will consider in this case so-called user-level DP. So user-level DP considers that the two datasets are neighboring if they differ only on the dataset of one user. So it's a stronger notion. Now you replace the entire dataset of a user instead of a single data point, okay? So this is a stronger notion, and I'm going to denote that the two datasets are neighboring, differing on only user case data by d tilde k d prime. And I'm going to denote by OK the set of messages sent and received by user k, which of course will depend on the algorithm that you are studying. And our notion of network differential privacy is as follows. We say that an algorithm satisfies epsilon delta network DP if essentially you take any user k and you are looking at the view of any other user L when the datasets are neighboring, so only differing in the data of user k, then you want this inequality, which is essentially the similar thing as in the general definition of DP, except that now you are concerned about the view of each user, right? So there is, in a way, some kind of filter on the output of the algorithm, which only keeps the messages that are actually seen by that user. And you want this to be true for all pairs of users KL. Okay, so this captures what we wanted, and you can see that this is a relaxation of local DP, because if OL now contains all the messages exchanged in the network, then this boils down to local DP. okay? So the point now is that depending on the algorithm, this OL will not contain all the messages, and hopefully you can show better guarantees under this definition. So let's try to use this definition to show better guarantees. To do that, okay, we needed to start somewhere, so we studied a very simple decentralized computation model, which is still used in many work, which is algorithm that sequentially update an estimate by kind of walking over the network graph, okay? So, for example, in the context of machine learning, it's like there is a user that initializes the model, makes an update, then sends it to a neighbor in the graph, and then this person will update the model using its data and then send it to someone else, and so on. This is the way you learn the model and update the model, okay, by having some kind of walk in the graph. So in this talk, I will focus on learning aspects. So in particular, we will see how to do decentralized SGD in this model and prove stronger guarantees than in the local model. In the paper, we also have results for more analytics, so computing private summaries of the user's data, like averages or discrete histograms, and so on. So again, I refer you to the paper if you want to know more about these algorithms. So let's focus about SGD and decentralized learning. Recall that we want to minimize an objective, which is the average of the objective functions, this classic objective. And we're going to consider a complete graph, okay? And so the algorithm in this complete graph is as follows. It looks like this. So from the perspective of users, essentially there is an initialization of the model. And then each user that receives the model will do a noisy stochastic gradient descent step, okay? In this way, so we draw some Gaussian noise with some variance, compute a gradient, add noise to it, and then do some kind of step. And then it will pass the updated model to the next user, which is selected uniformly at random, okay? And we continue like that for T rounds. Okay, so let's see what we can say about this simple algorithm. We need some assumptions of the function. So in this case, they need to be convex, Lipschitz, and smooth. And then what the result is saying, so I have stated it in a bit informal way because the result is a bit technical to state. But roughly what we have is this, right? So if for any kind of epsilon delta guarantee, you set the number of rounds of this algorithm to be at least k squared. And then you set the variance of the noise to be the one that you need for this algorithm to satisfy epsilon delta in the local model of differential privacy. Then you also have network DP, but with much better parameters. In particular, the epsilon is reduced by a factor log k over square root k, okay, which is nearly optimal because in the central model, you would get 1 over square root k, okay? So we are within a logarithmic factor of matching the utility of the trusted curator model. And so what this shows is that by decentralizing, you get privacy amplification by a pretty significant factor in the case of that algorithm, at least. All right, the proof, okay, is a bit involved, and it leverages recent results on things like privacy amplification by iteration. It also exploits, of course, a lot the randomness of the path that is taken by the model and that the participants can't see, right? They can only know when they receive the model, but they don't know where it went meanwhile, right, in between two visits to them. We can extend this to collusions also to some extent. And okay, even if the number of iterations is smaller than k squared, we still have amplification effects. We just don't have a closed form, but we can compute it numerically. And this is a numerical illustration, a little bit similar to the case with a server, where we see that in the case of network DP, which is the green one, we get values of an objective function and test accuracy that are essentially very close to the central model and much better than the local model. Okay? That's it. So I'm going to wrap up with maybe a few take-home messages to summarize. So the first thing, the kind of the starting point of this presentation was that not sharing data is not enough to ensure privacy, okay? And so we need to do more, and we need formal guarantees if we really care about privacy. Differential privacy is at least one popular way of formalizing this, and we have seen that it induces a privacy utility trade-off. There is a cost to privacy, and it depends on the trust model that you consider, like this central versus local model. And we have seen that in federated learning with a server, we can design protocols for differentially private aggregation that allow to achieve the same utility as in the central model for federated learning. while keeping the computational and communication costs quite low. And we have seen also that full decentralization can also alternatively provide you amplified privacy guarantees. And I kind of like this because in a way this is also providing a new incentive for using such approaches beyond the usual motivation of scalability, which is what people typically use to motivate these fully decentralized setups. That's it. Just a little bit of advertisement. I think probably most of you already know this survey paper that I was lucky enough to be a co-author with a bunch of authors throughout the world, like more than 50 authors. So this is a good way to keep up with Federated Learning. We have updated it in March, and it's been published in Foundation and Trends of Machine Learning. And then I'm also co-organizing an online seminar at Federated Learning, which is called Flow, where we have weekly or roughly weekly talks, usually on Wednesdays. And the videos and slides of all previous talks are available online. So if you want more Federated Learning after the end of this workshop, okay, there's probably more than you can handle there. All right, thanks a lot, and happy to take questions.
So are there any questions? Okay.
Thank you for your brilliant presentation. Beyond the maths, what is interesting is, in conclusion, to build up a framework of rational incentives to provide incentive for collaboration. There might be different economic models which encourage and both protect collaboration. Some of them are revenue sharing economic model on the protection and the exploitation of joint data. Others might be ways in which every individual try to optimize his own way and have the traditional frame of royalties. But what is important at the moment, we are in a country where people don't know how to cooperate, to collaborate. They have no clue or ideas about economic models. And they simply try to improvise with a frame where at the end they need guarantees from the state or from any protection of any mafia to go further. There are no real economic models with established frames of rule of the game to provide incentive for collaboration. How do you deal with this problematic?
Thanks for the question. So I think that goes way, way beyond the scope of my talk, although of course this is very interesting and important to have incentives for people to engage in these processes. So this talk focus was on privacy, and so I think privacy, being able to provide clear guarantees to participants is definitely part, I think, of the incentives that you need to give in many applications, at least for organizations or individuals to participate. So this is, I think, participating to this. Now, of course, okay, the more kind of economic models aspect of thing, I don't think, okay, I'm very competent to discuss this too much, but definitely those things are important in the long term if we want these things to be popular and used, including by citizens and companies. There is some work, so I can probably find a few pointers that I remember. I don't know the details of those works.
Okay, I think that's a very interesting point, and we can keep the discussion on that afterwards at lunch. We have another question online. So the question is, how do you keep track of the privacy loss across multiple training runs? So how basically do you ensure that you keep the privacy when you do multiple training runs? I think that was perhaps...
Okay, yes, so that's a good question. Maybe I went a little bit too fast on this. So indeed, okay, in the second case, we deal with directly we give a guarantees for the multi-rounds case. Okay, so the guarantee that you get depends on T, or more specifically, the amount of noise that you will need to add depends on the number of rounds that you will do. It's true that in the previous case, I focused on the sub-problem of computing an average, which is only one round, because in federated learning, then you do several rounds, so you need to compute several averages. And so the way you keep track of this is through composition. So this is what I was trying to convey here, the fact that thanks to this composition property of differential privacy, you can keep track of the privacy loss that across iterations. There are many ways to do that, and some tighter than others. So, okay, then we get into technicalities of how to keep track of privacy loss in differential privacy. There are, better composition results or ways to compose than others. But the main message is that you can do this composition. And so if you decide in advance how much rounds you will do, then you know how much noise you need to add at each round, or which privacy guarantee you need to have at the round level to get the desired guarantee at the overall level.
Okay, so thank you for that answer. And is there a last question, perhaps? Okay.
Thank you very much for your presentation. I was just wondering if you could give a bit a feeling of the differential privacy when it's on the dataset itself. I mean, perhaps I misunderstood, but I think in the last part of the presentation, you were speaking about the guarantee on the dataset itself and not the sample.
Okay.
And I'd like to know like how you feel it correlates to the sample, because in the end, I mean, you really want the guarantee on the sample itself, and I mean, right now I don't have an intuition on the link between the two, so please help me out.
I see. Yeah, this is a good question. Thanks for the question. So this guarantee at the dataset level, so you can see this as some kind of group level privacy. This is strictly, you can show that this is strictly stronger than the sample level, because with this definition, I'm able to protect or to make indistinguishable the fact of replacing an entire part of the whole dataset by another, instead of hiding the fact that I've changed one point. Okay, so basically you have roughly a factor size of the dataset in the strength of the guarantee, and you can convert these guarantees actually into sample level ones, and you show that there is this factor that you gain, right? And because of that, what you have to pay to get this is usually more, so you need to add more noise, roughly the size of these data sets, typically to cover for it. So this definition is stronger. Now, in practice or in practical use case, which is more appropriate really depends, right? If you have, let's say, hospitals with patient data, probably you don't want to hide an entire hospital, right? You don't want to protect the data set of a hospital. You want to give protections to individual samples which correspond to patients, right? So in this case, probably sample level is more appropriate. Now, if these data sets are user profiles, you know, maybe there are traces of users that navigate on the web or geolocation and so on, then probably you want to have user level privacy, because these points are correlated with one another. And so if you only provide sample level guarantee, you're probably not providing that much guarantee overall for a given user. Okay, so which one you want also depends, of course, on the use case. Yes, there is no difference. So instead of replacing one point, you can replace many points now and still make the output not too sensitive to that.
Okay, thank you very much again, Aurélien, for the talk.
Thank you.
So our next presentation is going to be given by Laurent Massoulier. So Laurent is a research director at INRIA. He's also the head of the joint INRIA and Microsoft Research Center, and an professor, part-time professor at École Polytechnique in CMAP. Laurent is going to present about decentralized learning, and especially the impact of delay and asynchrony in decentralized learning. So, yeah. Thank you again for giving the presentation.
use this mic. Yes, can you hear me? Okay, good morning. It's a pleasure to be here. I'd like to thank the organizers for having me and giving me this opportunity to speak. I will be presenting work done jointly with a team of colleagues at INRIA in Paris. I have put here the two archive references that I will be basing my talk upon. And this is going to be based on work especially done in collaboration with my two brilliant colleagues, Adrien and Mathieu, who are sitting over there. So you can talk to them afterwards if you like to. All right, so, okay, something changed on the sound, never mind. Okay, so I will be focusing on something that we have been seeing a lot already this morning, which is empirical risk minimization in a collective manner. So the setup is, as we've seen at least 3 times by now, as follows. We have a bunch of agents, each holding a personal or private data set, which is a collection of data points. And what we'd like to do is to train a model that fits this collective data set made up of the union of the individual data sets. And so basically we are trying to minimize a sum of loss functions, and we have a parameter x, and the minimizer that we are looking for is denoted x star, okay? And so we can simplify that and formulate it as the search for a minimizer of a sum of local functions held by each of the agents privately. All right, so the motivating questions that we are looking at today are as follows. We'd like to know how fast we can perform this optimization in a distributed manner, and either how fast or how cheaply, if we are concerned, say, with energy costs spent during the optimization. And so we want to address those questions and also in the process identify schemes that will allow us to realize this optimization at the cheapest or at the fastest. So a disclaimer here, I will not be talking about privacy or about statistical guarantees. I will be just focusing on this pure optimization problem. One aspect that we'll be particularly interested in is the fact that synchronous algorithms, which are very well studied, have undesirable aspects. In particular, if you do your distributed optimization in a synchronous manner, you are basically tuned or clocked to the slowest agent in the system, so that can be very detrimental. And also, in order to have operation run in synchrony, then you need to pay an overhead of synchronizing your agents. So our main interest is to realize this distributed optimization using as much as possible asynchronous algorithms, so going as far as possible towards a fully decentralized operation. All right, so my outline will be as follows. Despite our interest in asynchronous schemes, I will start by telling you quite a bit about synchronous schemes and the guarantees we can have for these. The reason being that it will allow me to introduce network models, the key parameters that do control our ability to optimize quickly, and also the concept of an accelerated convergence speed. Then I'll move on to the asynchronous setup, and we'll see that we can, to a large extent, have similar guarantees as in the synchronous setup. In particular, we can have fast optimization and ensure accelerated rates of convergence. And then I'll introduce another difficulty that we'd like to address, which is what about time delays? We know that in a real system, it takes time to compute a gradient. It takes time to communicate between two agents. And so we'll want to see how we can cope with those kinds of time delays in our systems and still get appealing guarantees. Okay, and then I wrap up with a couple of insights we get from our analysis. Right, so let's start with the synchronous framework first. For us, the network will be a graph consisting of a set of nodes which correspond to agents and of edges connecting pairs of agents between them. So as I said, each agent U has an associated function f sub u, and will distinguish the compute operations, typically agent U being able to compute a gradient of its local function, and will also rely on dual gradients, computing gradients of a conjugate function of the local function. And then we'll distinguish this from the communication operations where neighbors in the graph can exchange data. Let me mention a special case when the functions held locally are just the squared distances of the parameter vector x to some data vector theta u. Then the solution of the collective optimization is just the average of the individual vectors theta u. And so this specific problem has been studied quite a bit in the distributed computing literature, and it's known as the network averaging problem. And so people have been looking for a long time for schemes that are fast and that achieve this network averaging as quickly as possible, in particular in the asynchronous case. And the interest for this particular problem in distributed computing in part stemmed from functionality that is interesting in peer-to-peer, where you have a peer-to-peer network and each agent has only a local view. Agents may not even know how many agents there are out there. So by running this network averaging problem initiated by one agent starting with the value 1, all the others with the value 0, then once you have optimized, everyone has as a result the optimum, which is 1 over the number of agents. So that's a way to learn the size of the system, if you like, hence the interest in the peer-to-peer literature. Anyhow, so we'll be considering first synchronous operation, and for us that will be the following. We'll have operation in stages, and in each stage a node can compute, and that takes a t-comp amount of time, or it can, and then it can communicate, which will cost a duration t-com. Okay. Communication for us will be very simple. It will be what is also known as gossip. A communication round will be a round in which one agent receives a linear combination of vectors held by its neighbors, and so agent U will receive a linear combination of inputs of its neighbors V with weights LUV. We do have a number of technical assumptions on the L matrix, but basically for us, this L matrix is something that is very well studied in the context of graph theory, and this is the Laplacian matrix of the graph. So basically, an agent will receive a sum of differences of its own input with the inputs of its neighbors. And this can be either the standard Laplacian, or you could throw in weights, and that's the second expression that I have here on the slide. Conveniently enough, we will be able to summarize the hardness of communicating by a single parameter and the hardness of computing by a single parameter as well in our setup. And so the parameter measuring the hardness of communicating in our setup will be related to the structure of the matrix L that we use for communicating. That will be the so-called condition number of that matrix. And so for Laplacian matrices that we use, it's the ratio of the largest eigenvalue to the second smallest eigenvalue. And so as an illustrative example, for a complete graph, then this condition number is 1, which means that we communicate well on that graph. It's easy. Whereas if you look instead at a cycle graph over n agents, then this condition number is going to be n squared, and so this increases very fast with the number of agents. So this reflects the fact that the cycle is far less connected than the complete graph, hence the harder task of communicating along it. Okay, we'll make quite strong assumptions on the functions we consider, allowing us to capture the hardness of optimizing with a single parameter. We'll assume they are convex, and they are actually strictly convex with an associated parameter alpha, and then they are beta smooth. So these are standard assumptions in convex optimization. And so our measure of the hardness of optimizing is just the ratio of these two quantities, and that's the condition number of our convex functions. And so as an illustration, if we are considering the network averaging problem, this is a ratio of 1, which means that in a sense, this is an easy convex optimization problem. All right, so let's unroll a few results on the speed at which we can optimize in that setup. So first, this is, I guess, the 101 lesson in convex optimization. That's a gradient descent result. So we can have the following scheme where a user updates a vector of its local vector by subtracting the output of the communication stage based on gradients of the vectors of its neighbors, a very simple combination. And so that's an instance of gradient descent, and so we can apply standard theory, and we'll figure out that the error decays exponentially fast with a critical time, which is given by the time it takes to do one step, so tau comp plus tau com, the time to communicate once and compute once, multiplied by our two complexity parameters, the condition number of the functions and the condition number of communication. So that's expected, and this is what justifies these two parameters as measurements of the hardness of communicating or optimizing. So now we can leverage a celebrated result in convex optimization, which is Nesterov acceleration. So instead of maintaining just one vector, we have agents maintain two vectors, and we have an update rule for these two vectors, which is nearly as simple as in the first case. We do really very similar updates, except that we add momentum to our updates. And so, as a result, we are able to apply a square root to these condition numbers. And so that's acceleration, applying square root to the condition number. And this is meaningful. For instance, if we are considering our cycle network and we have 100 nodes, then n squared is 10,000. Applying square root is a speed up of 100. So this is very meaningful, and acceleration in optimization is an important ingredient if you are after savings in energy or in speed. Okay, we can do even slightly better in that setup. That's the last thing I want to mention about the synchronous setup. We are not constrained to do one step of compute per step of communication. And so if we are clever and rely on another celebrated object in optimization theory, which is Chebyshev polynomial, which has many nice properties, we can use this polynomial to inform a number of steps of communications between one step of compute. And so if we tweak the number of communication steps to the square root of the com parameter, then we are able to get a slightly better result where the communication cost affects the communication time and not the compute time. So this is really almost the same formula as before, except that we have a slight advantage, not penalizing computation in the same manner. So why do I mention that? Because we know that we can't do better than that. So that's as good as it gets, because there are nasty networks, cycles, for instance, or lines, and nasty functions for which there's no way you can optimize faster than that, okay? So in a sense, we have a good understanding of how to do distributed optimization in the synchronous framework. We have a good benchmark. On the other hand, this is clocked by the slowest node, as I said. So if you want to do that in a heterogeneous environment, you'll need to wait for everyone to compute a gradient. You'll need for every edge to have completed its communication. So it's really clocked to the worst speed in the network. So let's see what we can do in an asynchronous setup. What we'll consider is a particular way of ensuring asynchrony, which amounts to activate communications in a random fashion, independently for each edge in the network. So this is what we call the continuous time random activation model. And so an edge will be activated at random times with a frequency that is characteristic of that edge. That will be P sub UV for edge UV. And now we can enroll similar results to what we had in the synchronous case. So for instance, if we slightly adjust the notion of the condition number for communication, now this is going to be one over the second smallest eigenvalue of our Laplacian matrix, but with weights that are given by the activation frequencies. And we do each time we activate an edge, an update that is really the same as the ones we had in the previous scenario. So we update local vectors by a combination of gradients computed at the two ends of the edge. Well, we get a convergence time that is driven by the product of our two condition numbers, the computational one and the modified communication one. Okay, so that's what we can do in simple terms. Can we accelerate that? Yes. So here's how we do that. Instead of having a single vector maintained by each agent, now we have two vectors, as in Nesterov's acceleration. And so a formal description of what we do is as follows. We assume that the two vectors held by one agent are mixed continuously between updates, and the way they are mixed is described by an ordinary differential equation that I have written here. And then upon an activation, they do an update really much as we have seen before. So there's a gradient update and a momentum update. And so what we get as a characteristic time for convergence for our scheme is a square root of the product of our two condition numbers, and there's another term that that stems from the continuous time nature of our model here, which is the minimal activation frequency that appears also in our critical time. So a few comments on that result. I described it in a formal manner with ordinary differential equations. These are so simple that you can really solve them explicitly. So in fact, this can be implemented in an event-driven manner. And so this is really an asynchronous scheme. And the only synchronization that is hidden in there is that we assume, in order to implement that scheme, that nodes have clocks that count time at the same speed. Which is an assumption, but it's a fairly reasonable assumption, we believe, with modern devices. Another point to mention about this result is that this is actually a particular instance of a twist on Nesterov acceleration that we have come up with, which involves random coefficients in the original Nesterov acceleration scheme. And that is described and analyzed at length in the first archive paper I was putting on the title page. And just to recall, this is actual acceleration. So we have on the cycle network with 100 nodes a speed up of 100. So that's significant. There is a slight catch here, which is that to unroll this algorithm, you really need to have communications and computations that are very fast compared to the frequencies with which you perform updates involving a pair of nodes. So if you have very fast computations, very fast communications, that's fine, but Let's say we have you know, a starship is one of our agents, and it communicates with a satellite orbiting Earth, and it's on its way to Mars. Then we'll have non-negligible communication times, and we may have non-negligible compute times if we have very low-end agents. So we'd like to factor that in, understand the impact of those delays for computation and communication in our system. So that's what I want to do now. So here's how we are going to model the situation. We'll assume nodes in our system will trigger updates again at random times with some frequency p sub u for node u. And we'll assume that once it triggers some compute operation, then this will be finished by some time tau sub u. So there's a delay characteristic of an agent for compute. And similarly, we'll have delays characteristic of communication between agents for instance, a pair of agents uv will communicate at random times with some frequency p sub uv. And communication will complete by some time tau sub uv, okay? So let's describe schemes that we can analyze in that setup. Again, we'll have users maintain pairs of vectors, x and y. And so communication first. So if at time t minus tau sub uv, agents u and v decide to communicate, then the communication will be complete by time t. And so we assume that they will update their vectors by adding quantities that were available by the time the communication was triggered. So that's the time delay in the operation, and that's the equation I write here. So as you'll notice, the updated quantities pre-multiplied by some factor k sub uv for that corresponding communication, and this is the measure of how aggressively you adapt for that particular edge. We'll have a similar update for compute. I'm not detailing, but this is really of the same nature of the updates we've seen over and over. So if at time t minus tau sub u, node u decides to compute, well, it does so, and so by time t, it will update its parameter by quantities involving gradients that started being computed tau sub u units before. So this is the time delay characteristic. And again, we have some aggressiveness parameter here, k sub u, deciding how aggressively you update your quantities when you trigger a compute operation. And so we have, the architecture of a scheme and 3 parameters k that trigger the aggressiveness of the scheme, and frequencies p that trigger how frequently we invoke the scheme. Whereas the delays tau, they are physical quantities that we cannot control. So we know that in time delay systems, control systems, you cannot drive the system to where you want as aggressively as you can. You have to take the delay into account. For instance, when you tweak the temperature in your shower, you cannot converge to the ideal temperature very quickly. If you try, you'll oscillate between too hot and too cold. So here, how does that manifest itself? We cannot choose the aggressiveness parameters k as large as we can. We need to clock them to the reciprocals of the delays. And so we have conditions that specify exactly what we should enforce on those parameters. And so the result we have in that setup looks as follows. We have a notion of a complexity for communication, which is again an eigenvalue of a Laplacian, but this time the Laplacian is weighted by the k parameters, okay? And so what we get is something that is reminiscent of what we had previously. So we have a characteristic time for performing optimization with our scheme, which is the maximum of 3 characteristic times. And so let me ignore the last 2, but just mention that the first of the 3 terms is the one that matters, and it really looks exactly as we expect. So that is a product of a term measuring the hardness of optimization, kappa comp, and another one, which is this one over lambda 2 of k, which measures the hardness of the network for communicating and indirectly captures the delays in there. Okay, so a few comments on that scheme. It is implementable again in an event-driven fashion, so it's a really asynchronous scheme. Now we don't make any hidden assumptions on time delays. This is something that you can really implement in a system where communications and computations take some non-negligible time. The only synchronization assumption hidden in there is that, again, we have clocks that count time at the same speed at all nodes. Another thing to mention is that this characteristic time I've just described captures what we call the asynchronous speedup, namely, instead of having a kappa com clocked by the maximum compute time or the maximum communication time, it is weighted by the reciprocals of individual communication times. So this is how we get a much better speed than if we had a worst case assumption like we need to make when we do synchronized updates. Technical point, the assumption we need to make on our gains k sub u and k sub uv is in fact a very nice assumption. It can be rephrased, and it's essentially it constrains these parameters to a convex region somehow. So what this means is that if we try to optimize this scheme to achieve the optimization at the fastest with those delays, then we can just solve this convex optimization problem. So that's reasonably easy to do. And we'll be able to tweak the k parameters so as to drive our scheme as fast as possible to the optimum. So that's one thing we can do. So it's ready to tune somehow. It's a scheme that can be customized to various networks, delays, and so on. Another thing, if we're interested not in speed only, but also in energy costs, then maybe we'd like to measure energy costs for compute operations or communicate operations. So for instance, let's say we want to minimize the energy wasted on communications. Maybe this is captured by a weighted sum of the frequencies at which we activate communications. That makes sense. The energy spent per time unit. So this can be this justifies the following approach. We could say, let's try to trade off speed with energy cost, and let's try to maximize speed minus weighted energy somehow. And okay, so this is also something we can do. It's not a convex optimization this time, but this is an optimization we can do numerically. And this reveals interesting phenomena, and that's the last point I want to make. So we've tried that on a couple of networks. So networks on 30 nodes with random delays for communication, focusing on this network averaging problem. And so what we can do is try to reduce the energy cost by minimizing the function I was describing. And what we end up with is, in fact, sparser networks. So the optimization leads to removing edges from our graphs. Not only do we get sparser networks, but we also get a smaller energy expenditure. So that's the J parameter below the pictures. And we get either comparable speed or even faster convergence speed in some cases, in the case on the left in particular. So by tweaking the parameters, we can get a sparser network which wastes less energy and for which optimization can be made faster, which came as a surprise for us. And that's very reminiscent of something that some of you might have heard about, which is this Bryce paradox, which is a fact for road networks, that by suppressing a road, you can improve the flow of traffic in the network. I think the most famous example is adding a bridge to New York and then making the traffic far worse than without that new bridge. So that's a fact of life, Brace paradox. And so we have something that is not the same, but that is odd enough, that you can suppress communication links in your network and get better, faster convergence with fewer energy spent. All right, so to conclude, we came up with simple asynchronous schemes that only require clocks measuring time at the same speed. For the accelerated scheme, it was the first of its kind, because prior to that, there was no proven acceleration for the network averaging problem over any kind of network if you want to have asynchronous operations. So that was interesting in this respect. And the last point is that the delay tolerance scheme is something that you can really customize to the specifics of the network you are dealing with, the computational power of the agents, and so on and so forth. So in a sense, it suggests engineering rules to operate such a network. There are many open questions that we have on our radar. So how to combine the acceleration and the delay tolerance, this is something we don't know how to do yet. If we knew how to do that, we could be very close to having optimal schemes in terms of speed in this asynchronous setup. So far we don't have that, and so that's one of the objectives we are after. Thank you.
Thank you very much for the presentation. Are there any questions? Okay, so I have one at least. I'm very confused about this reduction of the size and improvement of energy. And so can you give up any kind of intuition on why it can happen? Because on the road example, I mean, it's also because, I mean, typically the speed of the cars on the road depends on how many cars pass by the road, and somehow, I mean, you create one road and everyone passes by that road and everyone is slower because of that. And is there any kind of analogy, or is just?
I'm not sure. I'm not sure. So I guess what I've not mentioned is what is it that we improve upon. So we started with a default setting where we decide arbitrarily that for each communication link, we will do updates at a frequency which is like 1 over the delay on that edge. And that is the common wisdom, that you should do that. You know, you have this delay, so you should do updates once every delay. So there's no particular reason why this is the right choice, but that's the default one. So maybe there's a part of the answer in there that this common wisdom is broken. So you should not really tweak your frequency update speeds like that. But yeah, I don't know.
Okay, thank you very much. Any other question from the room? Okay, I have just a very last quick one. How much of that is specific to deterministic gradients, and can you do more stochastic approach?
I guess so. In view of all the good work that Adrien has been doing in his PhD thesis, maybe you could use some of the techniques he has developed to do distributed stochastic gradient and bring it to this setup. And in particular, Adrien has a nice trick to do address stochastic gradient at nodes in a distributed optimization, which is to have augmented graph, which represents an agent by having a communication node and then dangling from that node one extra node per data point that this agent has. And so now when you activate one edge from that communication node to the corresponding data point, that is like doing stochastic gradient, picking that data. So we use that trick in our time-delayed problem. We deliberately split the compute and the communication steps by having a virtual node for communication and a virtual node for computation. And there's no reason why we could not have many compute nodes attached to one communication node, each compute node being responsible for one data point. I think following this line, maybe we can throw in guarantees for a stochastic gradient version of that.
Okay, thank you very much. Thank you again for the talk and the presentation. So it's now time for the lunch break. I think, I mean, we are restarting at 2, is that correct? And before that, do you want to provide some information, Mathieu?
Thanks. So we'll now move to the Sorbonne Center for AI, where we will have lunch. So we have Xavier Fresquet over here. So please follow him. He's our guide to this destination. It's about 5 minutes walk. There are signs along the way if you lose the groove at some point. And in any case, we'll regroup here at 2 to resume the session. Thanks a lot.
Okay. Shall we start? Okay. So welcome to this afternoon session. So there is a little change in the program. So Pascal Payet is not able to join us at the moment, so we'll swap the two talks of the session, and we'll start with the talk of Yann Favier, who we are delighted to have in this workshop, and who will speak about the legal aspects of federated learning and machine learning. So I leave the floor to Yann. Thanks for this talk.
Thank you very much. It's okay? Yes, for the microphone? Well, first of all, I would like to thank the organizer of this event, Hawkins staff, and Matthew Andrew in particular, for the invitation and the pleasure, the honor to be among scientists and specialists in computer science, statistics, applied mathematics, etc. So my point of view will be quite different. It will be that of a different kind of science, of scientist. A lawyer, mainly an academic one, specialized in personal data protection schemes with a specific approach to health data as sensitive data. Health data are a little much more than personal data. In the law, the constitutions, and in many international treaties on protection of fundamental rights, health is part of the person stricto sensu, and the law will tend very soon to consider this data, the health data, as elements or products of the person itself, with the same due protection. So that's the reason why, although in federated learning the main goal of this technique is to be in conformity with the rules of data protection and private life, in particular the GDPR, the question of compliance is still in debate for this particular kind of data mining. And we have to compose with specific questions and ethical issues. As we will see later, things are a bit more complex than it is for the vast category of personal data involved in the huge question of privacy compliance in artificial intelligence. But this is not the only issue. International property rights, and above all, the contractual relations between the players differ significantly between centralized data mining and federated learning. And the question is whether this is a new legal and ethical framework for federated learning. So let's start with some background information to understand the legal issues raised by these technologies. By the context, we'll see, I understand 2 points. First, the regulation around data and artificial intelligence in general. And second, the ethical issues directly related to professional practices, and especially, but not exclusively, with health data. On data-related regulation in general, and in the specific case of federated learning, nothing really happened by chance. When federated learning technology emerged in 2017, it was a year before the GDPR came into effect, and a few years before China's data protection law, the same year, 2021, this year, now. At the same time, the Artificial Intelligence Act in Europe was on track in EU institutions. And it can be noted that China's intervention in data regulation is based less on a desire to protect individual liberties than to regulate a market and operators who risk competing with the latter by analyzing data without state control. In these considerations, if this consideration of state control, of public control are not absent from the European legislator, it is necessary to agree that the whole European system is based on a theory of fundamental rights, which is crucial when it comes to interpreting this text that come from it. In comparison, the US regulations, with the exception of those relating to products and to health data, seem very sparse. The recent Californian regulation is very modest in this respect. But one should not forget the enormous resources of American constitutional law on these issues. So if we now focus on the GDPR, let's start by quick recalling the principles on which the European regulation is based, which I can recall is extraterritorial in application, not only for Europe. To point out the issues and the necessary adaptations in federated learning technique. As you can see, we have 6 principles in the regulation. Fairness and lawfulness. Lawfulness in the, yes, it's under the GDPR, controllers can authorize the processing of data simply, can't authorize, the processing of data simply because the data is available. They must be able to demonstrate the data processing falls under one of the 6 lawful bases outlined in Article 6 of the regulation in Europe. These 6 bases are consent, contractual background, legal obligation, vital interest, public task, and legitimate interest. One of them, one of the 6 lawful bases must be fulfilled. So you need to identify and state the lawful basis that applies to each data category processed. It's true that fairness is more ambiguous, is a more ambiguous term, but from a legal perspective, it is useful to consider fairness in the context of good faith. And processing data in good faith refers to using data in a way that you believe to be honest and legal. And transparency requires you to be not only lawful and fair in your data processing activities, but need you to let data subjects know what your processes include. And it's a critical way in the GDPR to fulfill the requirement to have a privacy policy. And the privacy policy needs to share core details about data practices, including the category of data, lawful basis for data collection, how you intend to use the data, how long you will keep the data, details of third-party relationships, whether the data leaves the EU, and privacy policy needs to match the reading ability of your target data subjects. As you can see, we have also the principle very important for federated learning of data minimization. The era of collecting massive amounts of data unnecessary is over. To address the issue of catch-all data processing tactics, Article 5 contains a principle on data minimization, which is crucial in federated learning. Article 5 of the GDPR say that data controllers may process data strictly using methods that are, I quote, adequate, relevant, and limited to what is necessary in relation to the purposes for which they are processed. If you can complete your core processing activities without the data, then you should never even go as far to collect it, much less process the data. Data minimization is a core, is a crucial in the technique in artificial intelligence. Accuracy of data is also very important. Article 5.1.d is clear when it says your personal data should, to the best of your ability, be accurate and where necessary, kept up to date. Every reasonable step must be taken to ensure that personal data that are inaccurate, having regard to the purposes for which they are processed, are erased or rectified without delay. As a result, it is a call to action for every data controller. And for data storage limits, Principle 5 in Article 5 say that the data storage principle places legal limits on how long data can remain in your database. And finally, integrity and confidentiality is defined as the process in a manner that ensures appropriate security of the data, of the personal data, including protection against unauthorized or unlawful processing and against accidental loss, destruction, or damage using appropriate technical or organizational measures. The first few principles related to security are related to integrity and confidentiality indirectly. For example, data minimization practices lower data subjects' risk of exposure in the event of a data breach. So it's very important that, as we can see in the regulation, in the EU regulation in Article 32, for instance, that data protection by design, like federated learning, refers to a design structure that builds privacy features and technologies into your project from inception or the initial design. That means following the data minimization principle as well as adding the appropriate technical data protection procedures like encryption and anonymization. So, in the context of federated learning, compliance with transparency and accountability in data protection by design is really very important. Transparency is full information provided to individuals in an accessible style and manner. Accountability is all organizations involved take demonstrable responsibility using personal data. And in the context of this protection by design is the data protection by design proposed by the techniques of federated learning. Federated learning limits the personal training data used to build the machine learning model to what is adequate, relevant, and necessary to achieve the purposes for which those data are processed. The data holder does not transfer the raw personal data used to train the machine learning model to another entity. So, training a model under the federated learning tends to avoid the duplication of personal data and contributes to reducing the risk. But the risk still exists, as we'll see later, and as we can see with the other presentation on the morning. So federated learning facilitates compliance with the principle of purpose limitation of Article 5 of the GDPR, and the resulting models are less vulnerable to membership interference attacks that models trained in a centralized fashion, like in the classical data learning. So it's important to know that some principle of artificial intelligence in EU regulation are on track. The European Parliament has undertaken a considerable amount of work in the area of artificial intelligence. In October, it adopted a number of resolutions related to artificial intelligence, including ethics, liability, and, it's very important, copyright. In 2021, those were followed by resolutions in criminal matters, education, culture, audiovisual sector, and the European Parliament resolution on a framework of ethical aspect of artificial intelligence, robotics, and related technologies specifically recommends to the Commissions to propose legislative action to harness the opportunities and benefits of artificial intelligence, but also to ensure protection of ethical principle. What sort of ethical principle in European regulation? Non-discriminatory access to data and the training of artificial intelligence algorithms on those datasets in a privacy preserving, secure, timely, transparent, trustworthy manner, and with an appropriate institutional governance. Relevant competent authorities, including sectoral one, providing or supporting the access to data, may also support the provision of high-quality data for the training, validation, and testing. So it's not really a detail to see that ethics is very important. Requirements for trustworthy artificial intelligence are proportionate obligation on all value chain participants, with enhance and promote the protection of the rights protected by the Charter of Fundamental Rights in Europe. Ethics. So ethics is crucial. Artificial intelligence technology and those who interact and are subject to them need to build an ethic by default and ethics by design regulatory framework on the basis of those principles that you can see here. It's from EU Parliament framework of ethical aspect of artificial intelligence, robotics, and related technologies. So it's principally a respect for human autonomy, prevention of harm, fairness, and explicability. Respect for human autonomy, prevention of harm, fairness, and explicability. So technical robustness is related to prevention of harm. Transparency of all elements relevant to an artificial intelligence system. The data, the system, the business models must preserve these principles. In the age of persuasive computing, transparency is critical to justify extensive data collection and its benefits to user. As you can see, some principles like diversity, non-discrimination, fairness are also very important in this new order of ethical legal frame. In order to achieve trustworthy artificial intelligence, you must enable inclusion and diversity through the entire artificial intelligence system. And as you can see, explainability in artificial intelligence systems requires that the decision made by an artificial intelligence system can be also understood and traced by human beings. Human in the loop is very important in this ethical framework. So, in the field of research, we can see that ethics in research is a little bit more than that. You can see also fairness and the problem of sources of bias. You can see also reproducibility and replicability as an issue, especially in federated learning. Conflict of interest and integrity are more classical in this in this field. And I would like to stress, in the perspective of federated learning, the importance of the principle, crucial in science, of reproducibility and replicability. The question and issues related to these two principles remain central. How should studies and other research approaches be designed to efficiently generate reliable knowledge? How might hypotheses and results be better communicated to allow others to confirm, to refute, or build on them? It's also a law issue. It's an ethical issue, but it's also it integrates the legal frame of artificial intelligence. So I just recall that reproducible research is research that is capable of being checked because the data, the code, the methods of analysis are available to other researchers. So the algorithm, for instance. Replicability is obtaining consistent results across studies aimed at answering the same scientific question, each of which has obtained its own data. And in the field of health data, we have more obligation. So as you can see, we have the legal frame of the GDPR about data protection. Then you have ethics in general. Then you have ethics in research. And then you have more with ethics in the context of sensitive data like health data. According to the Article 9 of the GDPR, healthcare data is highly, I quote, highly sensitive and must be protected accordingly following appropriate confidentiality procedures. So processing should be, I quote, necessary for reasons of public interest in the area of public health, such as protecting against serious cross-border threats to health or ensuring high standard of quality and safety of healthcare and medical products or of medical devices. So we have here a big issue in federated learning in the context of health data. More precisely is the second part, more specifically the legal issues in federated learning, what sort of issues we have that we don't have at the same intensity with artificial intelligence and data mining centralized, in the centralized manner. The questions are very, very important and very technical and very complex. Who is responsible, for instance, as the training stage? What about liability and property issues? Property of the data, property of the results. What are the specificities of the platform and what is the impact of training? And finally, how to implement the regulation, the European regulation about the data. So, if you see this picture, you can see all the problem we have at a legal for a legal frame, to build a legal frame for federated learning. And the structure, the scheme is very, very specific. And the difficulty is to identify all the relations, all the legal relations we have between the actors. So we have an issue in data protection. We have an issue in about the contractual links. You have an issue about intellectual property, about liability in general, and we don't have at this time all the answers to this question. So it's very important for us as jurists, as lawyer, as academic in law, to really study the problem and to answer to this question. And we don't have all the answers about this. And we are, well, studying, for instance, the GDPR compliance in the context of federated learning about the participant roles between data subject and data controller and data processor. What differences in the context? Other question is the GDPR when it obligates data controllers to provide fundamental rights to data subjects to control over the data. How does it work? What type of contractual relation you can build in this context? And finally, what's the purpose of data collection? Or what are the purposes of data collection? It's the main issue too in this context to define between the different actors what are the purposes they have. Is the purpose is common, is different. We have a different issue in this regard. What data is adequate? How to consider the limitation? What is relevant before executing an algorithm in this context? All these kind of questions are now on track with lawyers, with academics, and we are trying really to answer technically to all these questions. In federated learning, processing data in this context may be quite complicated. We have, for instance, to determine if training a machine learning model with federated learning qualifies it as a processing of personal data wholly or partly by automated means, say Article 2 of the GDPR. If we are really in the context of this definition, the raw training data provided by the data holders qualify as personal data, the operation performed on such data in the federated learning process. And therefore, under the material scope of the GDPR, using the raw training data provided by the client, for instance, an hospital, on processing data patient, and the processing operation performed on this data are likely to qualify as a processing under the GDPR. Training a machine learning model using the federated learning approach does not necessarily exempt all the processing operations occurring in the federated learning framework from the application of the GDPR. This requires that the processing rests on one of the legal grounds listed in Article 6 I mentioned first in this presentation, and to list the purposes of the training and to verify if the purpose is compatible with the purpose for which the data were originally collected. So it's very complicated to know whether the operation performed on the model updates derived from the raw training data are in the material scope of the GDPR. These updates may, in certain cases, reveal information about the underlying personal training data. This means that they may qualify, it's not certain, they may qualify as data relating to an identifiable natural person, say the GDPR under the Article 4.1 of the European regulation. Well, as you see, the question is very complex, and federated learning it's true that federated learning facilitates compliance with the principles of, for instance, data minimization of Article 5.1 of the GDPR. But the principle requires the data controller to limit the personal training data used to build the machine learning model to what is really adequate, what is really relevant, what is really necessary to achieve the purposes for which those data are processed. So it's not very simple and not very, it's not described in the European regulation. So the European institution and the European Data Protection Board built some guidelines to interpret the European regulation with, in consideration of the new techniques operators develop for privacy by design, like federated learning. And as we see, regarding the rules, we have some points more precise in these guidelines. For instance, a controller must use processors providing sufficient guarantees to implement appropriate technical and organizational measures. All actors shall, in a transparency manner, determine and agree on their respective responsibilities for compliance. All actors, not one. Any processing of personal data by a processor must be governed by a contract liability by contract. Very important to build some contractual structure between the actors. Any proceeding of personal data by a processor must be governed by a contract or other legal act which shall be in writing, including in electronic form, and be binding. So a sort of imperativity in this context. So the question must be to know if, in the context of federated learning, every actor is a joint controller, for instance. Is the model different from what, say, what we can read in the GDPR, the controller alone or jointly with others, the purposes and the means of the processing. The processor processes personal data on behalf of the controller. All these articles are not very adequate in relation with federated learning technique. So the GDPR is based on the controller-processor distinction. Is this distinction still relevant in the context of federated learning? It's a question. And the broad interpretation of the notion of joint control is described in the recent ruling of the Court of Justice of the European Union in 2019. And it's a very large interpretation. So, recent guidance by the European Data Protection Board on the concept of controllers and processor must be known to develop the legal framework. And in the context more specialized in Earth data and research, we have very big issues. Privacy and performance, for instance. Is it compatible? As we see in other presentation this morning, federated learning does not solve all potential privacy issues and will always carry some risks. Privacy preserving techniques for federated learning offer a level of protection that exceed today's current commercially available models. However, these techniques may affect the accuracy of the model. And furthermore, future techniques and ancillary data could be used to compromise a model previously considered to be low risk, but it's not. In federated learning systems that operate on larger scales, it might be impractical to establish an enforceable collaborative agreement. Some clients may deliberately try to degrade performance, bring the system down, or extract information from other parties. Security strategies will be required to mitigate these risks, such as advanced encryption of model submission, secure authentication of all parties, traceability of actions, differential privacy, verification system, execution integrity, model confidentiality, protections against adversarial attacks. So it's not very easy. What about research purposes? Earlier this year, the European Data Protection Board issued additional guidance for the application of the General Data Protection Regulation in Europe in the area of scientific health research. It's very recent, this year. Confirmed that the informed consent that individuals must provide under ethical standards to participate in scientific research is to be distinguished of the general principle of consent in the European regulation. So as you see, the context of federated learning is very complex, and the European regulation does not really bring all the answers that specialists can see in the application of this principle. Thank you very much for your attention.
Thank you very much, Jan. Thank you for this very broad overview of the legal questions surrounding the activity in machine learning and especially federated learning. So we've seen there are lots of questions around. So I suggest that we discuss further the topics during the coffee break, and we pass the mic to the next speaker. Thanks.
Okay, perfect. Thanks for having me. I'm very honored to be here. So my name is Pascal Payet. I'm a cryptographer. I'm also the CTO of a company called Zama. And today I'm going to talk about homomorphic encryption, which is a kind of a rising star among these new crypto technologies that are on the horizon and which we think can change the security of the cloud completely, in particular for machine learning applications. But just to start, maybe I can ask you guys in the audience, how many of you have never heard of homomorphic encryption before? One, wow, two. All right, so I'm pretty impressed that you guys already know about this crypto technology that I personally find absolutely fantastic. So in this talk, I wanted to give you like the latest news about homomorphic encryption, but also some kind of an overview of what it is. So maybe there will be some parts that I will skip if you're already familiar with it. And then I will address what we can do with homomorphic encryption when we're considering machine learning applications. So maybe I'll be quick on this, but for the two people who are not familiar with it, or for our audience on YouTube, so what is fully homomorphic encryption? Well, fully homomorphic encryption is some kind of technique by which you can basically, so I assume you're familiar more or less with encryption. So with encryption, you have a data X, and you encrypt it under a certain secret key, SK here, the red key. And then you get an encryption of X, right? So something that usually you cannot do anything with the encryption, basically. What we're familiar with is the notion of encryption, where once you've encrypted data, the encrypted data just sits there. So you can just send it over the wire, you can just store it, but you cannot do much with it. With homomorphic encryption, the paradigm is completely different. You can process encrypted data directly. So it means that given the encryption of X, and given a public key that is coming from the user, so the user has two keys, the secret key for both encryption and decryption, and a public key which is for evaluation. So it's a public key, but it's a symmetric key system, which is a bit confusing because in crypto usually we talk about public key encryption, which means we can encrypt using a public key, just the one who decrypts as a secret key. But here it's secret key encryption, but there's still a public key just for evaluation. So as a user, you generate a pair of keys, a secret key for yourself to decrypt and encrypt, and then you generate a public key that you give to the cloud, for instance. You can upload encrypted data in there, and then the cloud is going to be able to process this data. And what is fantastic is that we can now, with the current state of the art in homomorphic encryption, we can actually process like any Turing-complete circuit, which means basically any function on this encrypted data, which is fantastic. And basically, cryptographers have been after this for decades, almost 50 years. So it's a very exciting time for cryptographers, but also for practitioners who want to use this to basically secure the cloud. So once you, of course, the cloud is going to compute this function, apply this function homomorphically over the over X encrypted, but nothing gets decrypted in the process, right? Every intermediate variable is going to be processed encrypted. The cloud doesn't know how to decrypt. It just knows how to manipulate encrypted data, add numbers, multiply numbers, apply functions, and in the end, it comes up with this f of x value, except that it's encrypted. The only thing the cloud can do is send that back to the user. The user decrypts with her own key and then recovers f of x. So this is really fantastic as a principle. Of course, I'm not going to go into the gory mathematical details of it. I'm just here to give you like a sense of what we can do today. I was saying before, there is the classical notion of public key encryption, where you're given when the key is generated, you generate also a public key for encryption. And this is the case here as well. There is another flavor of homomorphic encryption where instead of having the same secret key to both encrypt and decrypt, you can have a public key for encryption as well. So the user generates a secret key for decryption, and then there are two public keys, one for encryption, one for evaluation. This is a little bit theoretical because in practice, the two public keys are like very highly, they're like sub-pieces of the same public key, actually. But what is very interesting is that, we know that there is a big disconnect in the theory of encryption between symmetric key systems, where you use the same key for both encryption and decryption, and regular public key encryption schemes, where you have a public key for encryption and a secret key for decryption. We know that the two are not equivalent. And there are like theoretical foundations that explain why. But what is very interesting is that in the case of homomorphic encryption, so you have also these two flavors with a public key to encrypt or not. And actually they happen to be equivalent, which already shows that homomorphic encryption is not a normal crypto object, like it's something that has superpowers. And so usually we start by building something that is symmetric key, use the same key for both encryption and decryption, and then there is a generic way of generating a public key for encryption. So the vision that you can build, knowing that you can instrument homomorphic encryption, is that, as I said before, there is a notion of a client and a server, and the client can basically encrypt everything, send everything encrypted to the server, and the server will do all the heavy lifting of computing, of applying algorithms, without ever seeing the data. So it's a very eye-opening functionality for those who have worked for years on trying to secure the cloud, right? And you can think of plenty of use cases where this is useful, basically health data, but also like any kind of financial data, government data, crime-related data, and so on. So you can just imagine to a cloud operator, a service operator that would operate some kind of value-added service and would never see the data, and because the data would be encrypted by users. So the benefits are obvious, like the privacy is enforced. You cannot basically steal user data without their consent, because now if you want their data, they will have to consent to give them to you in the clear. And there's also, so it puts back the user in the center of the picture, in control of her own data. And this is like a transformative thing compared to what we do today. So we can, so the cloud learns nothing. There are no possible data breaches because all you can steal is encrypted data, so basically useless. And it's irrelevant what the server is, so you can just delegate your homomorphic computations to like a server somewhere in India or in China or somewhere. You don't care anymore about the location issue, the geolocation issues, the laws that apply in the country in which the server is running, because you don't care anymore, because there is no critical asset to steal. So you don't care, you can just minimize the costs. So this is a very promising technology for the future. And at Zama, we have a little bit this very long-term vision, which called HTTP-Z. So it's a little bit of a concept that we need actually to refine. But the idea is that there's been HTTP, right? Then there's been HTTPS, which just adds a layer of authentication and encryption for all the data in transit between you, the client, and the server, right? But again, as I was saying, once you have encrypted data, there's nothing you can do except either decrypt it or store it. So it's just protection of data at rest or in transit. With homomorphic encryption, you can actually process data, right? So it means we can think of a future of the internet which we call, facetiously HTTP-Z, where as a client, your browser indicates to the server that it would like to access the homomorphic computation services offered by the server. And then all the data that would be exchanged would be actually end-to-end encrypted by the user and processed homomorphically by the server. So the server sees nothing, but still operates the added value service. And so if you follow my line of thoughts, probably you have like machine learning and inference services in mind. So I'm going to come to that in a moment. First of all, I wanted to give you a sense of what's going on in that space. And so it's been like decades. I think the first ever thought about homomorphic encryption was under a different terminology, was privacy homomorphisms. So run reversed. So we're talking like the late 70s. So the idea is actually very, very old. Then we had like about 30 years of what we call partial homomorphic encryption, which means we cannot support, it's not Turing complete or circuit complete. We cannot support all the operations on encrypted data, just like one operation. Like we can add a bunch of encrypted numbers, but the only thing we can do is add them or multiply them by constants, like multiply by 2 or 3, which is basically like an addition. Or you can multiply a bunch of encrypted numbers, you can multiply them, but you cannot actually add them. So we never had an example of an encryption scheme which would support both operations at the same time. So you would have to pick like one system for addition and then another system for multiplication. And the holy grail of this was to find a way to reconcile both operations in the same encryption system. And it wasn't until 2009 that that Craig Gentry, so a guy from IBM, actually found a theoretical solution and published it in a crypto conference. And it was a big eye-opener because a lot of people, including myself, I carried out my PhD specifically on this subject, were at that time thinking that there was somewhere an impossibility result to be found, that it was, this holy grail was too good to be true, that it couldn't be realized ever. And so it was this eye-opening moment where suddenly a lot of people in the community were surprised by this existence. So it was terribly inefficient, right? But it showed it answered the question of existence. And since then, there's been like several branches of the field, several ways how to construct fully homomorphic encryption, fully in the sense that you support both operations, additions and multiplications. You can build pretty much everything on top of that. So at this point in time, there are essentially two branches. I would say the leveled approach and the fast bootstrapping approach. So I'm going to give you a little bit of a sense of what these mean, so that you can relate if you see articles, or even if you're not a cryptographer, these concepts are pretty okay to grasp. I mean, you don't need to dig into the gory details to understand actually what's going on. And so Zama, the company that we co-founded about a bit less than 2 years ago with my co-founder, is actually focusing on one specific fully homomorphic encryption technology, which is called Taurus FHE. Okay, so it is now common to identify several generations of schemes. So we're not even talking about partial homomorphic encryption, the systems that were supporting just one operation. So the first generation was these very early schemes, and then second generation, third generation, and we estimate that we're in the fourth generation. This is debatable, depending on where you want to draw the frontier. But this is approximately what is going on. And every time there's been like drastic changes in efficiency, and we've gained like several orders of magnitude in terms of efficiency, which is spectacular. Over the course of, from 2009 up to today, basically, we're on the verge of being able to put that in production and having homomorphic applications running in the cloud. And so I'm going to share exciting benchmarks after talking about homomorphic encryption. So the first generation of FHE was, everything was, you can decompose like any data into bits, right? Into individual bits. So Gentry's idea was just, okay, you decompose everything into bits, and the only two operations that you need to support to be circuit complete is to support a XOR and an AND, right? If you can multiply 2 bits modulo 2, if you can add 2 bits modulo 2, you can build an OR, you can build an AND, you can build a XOR, an XOR, an AND, an OR. You can build all the Boolean gates out there. And then, of course, with Boolean circuits, you can basically support like any computation, right? The problem was the addition was reasonably fast, but the multiplication, mode 2, the AND, was like super slow. Like it would take like 30 minutes to just multiply 2 bits homomorphically. I'm not hearing laughs. You should laugh at this. Fortunately today, we've made drastic progress. And the problem, I mean, the concepts that were introduced with Gentry scheme was essentially that there is a notion of noise attached to ciphertext. And you cannot really get rid of the noise, otherwise there is no security for the encryption. You can actually break the encryption, recover the key. But you need a level of noise. So what does it mean exactly? It means when you encrypt X, you have to put some randomness in there. The randomness has to be there. And the amplitude of this noise, of this random number that you've used to encrypt your data, has to be below a certain threshold, which we symbolize here with a thermometer. So as long as the level of noise is below the threshold, the ciphertext is valid, meaning that you can decrypt it with the secret key, and you will recover X. The problem there is if the noise exceeds, like overflows, exceeds this threshold, then the ciphertext is not valid anymore, meaning that you decrypt, but the value that you decrypt will be incorrect, right? And the thing is, the noise accumulates over time. So if you start aggregating ciphertexts, their noises are going to be aggregated together in the resulting ciphertext. And so the noise can only grow over time as you do homomorphic computations. And at some point, if you reach this threshold, you're losing the correctness of your computation, right? And so that was the big problem that Gentry faced. I'm going to talk about how you can solve this problem in a minute, but essentially what Gentry was showing that when you compute a homomorphic addition modulo 2 of 2 bits, the noises in the input ciphertext are basically going to be added. So if you had 2 numbers, the size of the addition of the sum will not grow significantly. I mean, if you have 2 noises of the same size, you add them together, maybe you have 1 carry bit, but essentially the size is the same. But when you multiply basically ciphertext, what happens is that the noises, the random values are going to be multiplied. So once they get multiplied, of course, the size of the result like doubles. And so every time you multiply 2 bits, the size of the noise is going to grow exponentially, right? So if you're given a certain circuit, a Boolean circuit here, and you have like a level of multiplications, if you measure the number of multiplications you go across to do your computation, the noise is going to grow exponentially along that path. And like it was like a terrible like observation that what are we going to do? Like so the noise grows exponentially, and when you reach this threshold, you lose correctness. So maybe this is an unsolvable problem. But the genius idea was to invent the technique of bootstrapping. And bootstrapping is actually a very neat concept that you can easily describe. Of course, again, there are like details behind that. But the idea is that you take an encryption of X. So the orange box over there over X means that it's encrypted, like protected with an encryption envelope. Well, yeah. And there's this thermometer that says that the noise is acceptable. Like this ciphertext is still valid, it's still encrypting X, right? And so you do a number of operations and you end up with an encryption of Y, you know, the result of a computation over X, and the noise is just under the threshold. But if you would do like one more operation, the ciphertext would become invalid. So there is nothing much that you can do, but you can use bootstrapping to kind of reset the noise level in the ciphertext of Y. And to do that, what you do is actually, so symbolically, because there are shortcuts in there, but what you do is you take this encryption of Y, you over-encrypt it with another key, where instead of using the orange key, you're using the blue key, and with a low level of noise, right? So now you have this Y value that is doubly encrypted. It's a double encryption. And then what you do is that you take the orange secret key, but encrypt it under the blue key. Okay. And what you do is you apply the decryption circuit homomorphically, which you can do because basically the decryption circuit is taking the orange key, the secret key, as well as a ciphertext, the Y with the orange box around it. But since you do it homomorphically, they are both encrypted under the blue key. And so you end up with, when you decrypt the encryption of Y with a secret key, you end up with Y. And so you decrypt homomorphically. So there is still the blue envelope on top of it. And so what you end up with is basically another encryption of Y, but this time the noise only depends on the depth, the multiplicative depth of the decryption circuit. So it is still independent from the input noise, the noise with the yellow noise out there. So so if you follow this paradigm, you can actually reset the noise if you assume that the user can generate like multiple keys, and you can play with this. So it's kind of fantastic. Once you've reached a certain level of noise, you're just going to bootstrap. You have a fresh ciphertext that hasn't changed in value, and then you go on with your homomorphic computation. So theoretically, you can go on forever. The problem was, well, it's super slow, and it would take forever to do this. And so that's why there were these two approaches. The somewhat homomorphic encryption approach and the real fully homomorphic encryption approach. So the somewhat homomorphic encryption was, oh, sorry. So this is actually the fully homomorphic encryption. Maybe I can display both at the same time. Yes. So the somewhat homomorphic encryption is on the right. It's where you do a Boolean circuit, so the noise is going to grow exponentially in there, but you try to generate the parameters, the crypto parameters, in a way that at the very end, like the blue dots at the end symbolize the outputs of the circuit, so that they're actually full of noise. They couldn't bear just another homomorphic operation, but you don't care. You stop there, you send that back to the user is going to decrypt, right? So you never bootstrap, right? You just do homomorphic computations. It's just you're generating parameters, you're setting parameters so that the you allocate a lot of budget for the noise. So the noise can grow, and you predict how much noise, what is the budget you need to grow, to go across the entire circuit. But you never bootstrap, right? And then Gentry had this initial vision, which is, okay, on the contrary, I'm bootstrapping like every time. So I'm not allowing the noise to grow like ever. Like when I'm doing an operation, be it addition or multiplication, essentially, I mean, super useful for multiplication essentially, I'm going to bootstrap right away. So I'm using like shorter parameters, but I'm going to bootstrap at every operation. So the advantage of this is I can go on forever, right? Because everything is on the left is always, all the ciphertexts are always very fresh. So you can go on with, composing computations, and there is no, you can go virtually at any depth in the circuit. And of course, you can use like a mix of these two approaches. I would say these were like the two ends of the spectrum. And then in the second generation, something happened, which is instead of having the noise doubling, which triggers like an exponential growth, we can flatten this growth back to linear, which was a big breakthrough at the time. And after that, there were like other things that you could do, like using batching or packing, meaning instead of having a ciphertext that encrypts just a single bit, it would encrypt a vector of bits, right? So every ciphertext would encrypt a vector of bits, and when you do operations, you do all the operations like in an SIMD fashion. So you can vectorize operations without essentially modifying the length of the ciphertext, and so that would give you like the notion of batching or vectorization, and a lot of speed up with this. Okay, there's been a third generation never used, never implemented because it was actually very slow. And then there was a fourth generation, which is Taurus FHE, which is the system that we're using in currently in Zama. So what we're doing at Zama is everything that we build is open source because we're strong believers in elevating the ecosystem of developers, like empowering them with tools. Right now, if you want to do a homomorphic application, it's excruciatingly difficult, even for cryptographers. So what we want is to build like a series of tools that that can be used without any prerequisite knowledge of cryptography whatsoever. So you're just a developer, you find homomorphic encryption is cool, I would like to do a homomorphic application. Right, so you can just download our tools and then work with them with tutorials and webinars and so on, and you should be able to do that on your own. And we strongly believe that generalized adoption of homomorphic encryption will only happen if we can like have standards for crypto techniques and at the same time have open source tools that are very, very easy to use. And this is the current problem, I would say, in the adoption of homomorphic encryption. So there are quite a number of FHE libraries out there to support homomorphic computation. Some support certain schemes. Some you have to bring your own parameters, which is another thing. Like it's very difficult to issue parameters, and they heavily depend on the use case and so on. So in Zama, we're developing what we call the concrete framework. So there is a concrete library, there is a concrete compiler, and there is like a concrete ML front end as well. And so the main improvement that we're using is something that is called programmable bootstrapping. Just to give you a sense of, so maybe I will skip this part for now. Okay, so I presented Gentry's bootstrapping, this brilliant idea of bootstrapping to reset the noise. So basically when you do the bootstrapping again, you end up with an encryption under a different key of the same value X, right? And the noise, you see the thermometer here, so the noise is reset. Perfect. What we call programmable bootstrapping is actually a technique that allows you to apply a function at the same time that you're resetting the noise, and basically for free. So you have this encryption of X here in input as before, and it's just during the bootstrap operation, you can have an auxiliary input, which is a tabulated function, right? So it's basically a table lookup. But this is completely pre-computed. And you give this lookup table to the bootstrap operation, and what you end up with is the encryption, the refreshed encryption of f of x, right? And what is very, very attractive is that the efficiency of this bootstrap operation, I mean, it just requires a few milliseconds or a few tens of milliseconds, but at the same time, it does not depend on the complexity of the function f, right? So it can be like heavily nonlinear, it doesn't matter, because basically it's tabulated. So you can do a lot with this. You can do a lot with this operation. And okay, so this is essentially the principle that the function is tabulated. So for instance, we cannot like do a native multiplication with TF-HE. So TF-HE can encrypt bits, but also integers, even real numbers. But it doesn't support like the native multiplication. Unfortunately, you can, given an encryption of x and of y, you cannot get an encryption of x times y. We've been working on that recently, so we have results that are going to be published at AsiaCrypt, so it's coming, but natively it wasn't supported. But a way you could use programmable bootstrapping to do that is you take an encryption of x, of y, and you have this, you know, in the black square there, you have this identity, like if you want to compute the product of two numbers, you just need to apply the essentially the square over the sum and their difference. And because of that, you can just program the function square over 4, and additions and subtractions are basically for free, right? They're very easy to do. But using these two bootstrapping operations by programming the same function and computing the difference, you can actually compute the product of x times y. So it shows that you can actually do, it makes you like super powerful to have this primitive of programmable bootstrapping. You can compute a lot of things that used to be very difficult to do homomorphically, that would cost a lot of time. And the same thing for the division, same thing if you want to compute the norm of basically a vector. And again, you can apply programmable bootstrapping in the context where you have univariate functions, right? So yeah, so every time you have to decompose your operation into univariate functions, but any function will do. And there is I would say, a theory behind that. Actually, there is something called the KST, the Kolmogorov superposition theorem. Bear with me, I'm going to come to machine learning in a minute. But this KST theorem says that any multivariate function can actually be decomposed into a network of univariate functions and additions or linear combinations. And so this is very powerful. So it means you can, if you have like like any computation over a vector of variables, you can always compile this multivariate algorithm into a network of univariate functions and linear operations. And then you can just, for every function, apply programmable bootstrapping, and the linear parts are super easy. So basically, what we're building in the long term is a way to compile any computation using this paradigm. So it's much better than the Boolean circuit paradigm, because it's way more efficient, like by orders of magnitude. And what is very appealing here is the application to machine learning, which now is trivial, right? if you look at a neuron, what it does is a linear combination or a fine combination of input variables, and then we obtain the result, which is a multisum, and then we have to compute this activation function. So in the past, people like at Microsoft, for instance, invented this approach, CryptoNets, where what they were doing is instead of having like a normal, normal for somebody in data science, a normal activation function, they would replace it with the square function. Because homomorphically, a square is just one single product, so it costs less, right? So they would train neural networks with this crazy activation function, and interestingly enough, amusingly enough, it would give like pretty decent results in terms of machine learning. You would have a pretty decent accuracy if the network is not too deep. And but in our case, so that was used by the CryptoNets paper a few years back. But in our case, we can just program this function. We don't care if it's a sigmoid, ReLU, or whatever. We can just use programmable bootstrapping because it's a univariate function. And so we do a fast bootstrapping at every neuron, and we can go as deep as we want because at the same time the noise is being refreshed. So we can go super deep and have like deep learning supported homomorphically, which is like super exciting, which could not be done with the CryptoNets approach. So to report, like, so these are, so we have like updated benchmarks, but essentially you can see like, so we've applied this to a neural network of 20 layers. If you compare with CryptoNets and similar approaches, you can go up to maybe 12, 15 layers at most. With our technique, we can go as deep as we want. So we played with a neural network of 20 layers. The important thing here is the number of layers. This was like the main challenge, right? It solves the MNIST use case, so no use for machine learning. It's just like to show that what homomorphic encryption can do with machine learning. But we're working, of course, in improving the efficiency and also expanding to real-life neural networks. But essentially, without costing too much in terms of accuracy, we can convert the neural network into a homomorphic equivalent that will run in seconds, either on a local CPU on your laptop or over a multi-core server on AWS. And what is like super exciting is that we had like the first ever homomorphic neural network for 50 layers, and we went up to 100 layers, but there is no theoretical limit. We can go as deep as we want. The efficiency will highly depend on the parallelism that you can support, on the machine on which you run the homomorphic inference. And also we're thinking about using GPUs. We're not only thinking, we're working on GPU implementations as well as FPGA implementations with partners so that we can boost everything using hardware acceleration. So to finish with this, I would say that, so this is a little bit outdated, but at this time, what we build at Zama is an open source framework, the concrete framework, that comprised this plugin-based homomorphic library. Plugin in the sense that you can plug basically a driver for a normal laptop CPU or desktop CPU, but you could actually use also the hardware support for a GPU or multiple GPUs, FPGAs, maybe A6 in the future. But at this point, with all the progress that has been made with fully homomorphic encryption, we still need some hardware acceleration to get to homomorphic supremacy, which is this vision where basically you lose like a factor at most 10 when you do things encrypted versus what you would get if you would do everything in the clear, at which point the crypto is not a problem anymore. It's more about data in transit, these kind of things. It doesn't change the user experience, so it would be used by everybody like by default, which is a little bit our vision. But to get there, we need to build like a very usable tools that any developer can actually use and build things with. And this is, for us, this is our main objective. Okay, I think I'm done. I don't know if you have questions.
Thanks a lot, Pascal. So any question, comment? Yes.
Hi, thank you very much for your talk. I have a question. Is it all those protocols robust to quantum computers, or will they fall once quantum computers are on the market, like the asymmetric cryptography?
I'm sorry, I didn't get that. Are you asking me if homomorphic encryption resists quantum computations? Okay. So yes. As a matter of fact, it's a big issue now, quantum computers, because they're appearing on the horizon. We don't know exactly how far, how long it will take to get them on your desktop, but there's a big sense that they're coming. And in the crypto community, there's a lot of work also with standardization bodies to standardize as quick as possible replacement algorithms that are quantum resistant. But fortunately enough, the kind of, I would say, the kind of mathematics or algorithmics that we're using to build homomorphic encryption is already by nature is already quantum resistant. So the typical algebraic settings that actually are destroyed by quantum computers are factoring-based schemes or discrete log-based schemes. These schemes are all over the world. You're using them if you're using a carte bancaire, or if you just with your phone, right? You just use them like every day. But so these are the ones that we're trying to have replacements for as soon as we can, and this is like coming. But we don't have to do this effort for homomorphic encryption because we're precisely reusing. There's a big intersection between quantum-resistant encryption schemes and fully homomorphic encryption schemes. They rely on the learning with error complexity assumption. So they're already like future-proof by nature, which is which is an additional, very nice feature.
Okay, thank you.
Hi, thank you very much.
Sure.
You said earlier in your talk that we're right on the brink of homomorphic encryption being ready for commercialization.
Yeah.
What is it? If we're on the brink, what do we still need?
What is? Sorry.
What do we still need if we're on the brink of being ready?
Right.
What in addition do you need?
Oh, you mean the roadblocks?
Yeah.
Like what is preventing us from going there like today?
Yeah.
Or overnight? So I would say there are several things. There are plenty of factors. So one factor is, so FHE has been a holy grail for cryptographers, but hardly known outside of the crypto community for the last decade. Now it's getting more popular. Big companies have announced that they would like to offer services in that space. So IBM has made an announcement for this. Intel has made an announcement. Google, so every month we organize a meetup on fhe.org, and the last one, Google presented their transpiler that also was based on TFHE. So there is some momentum. We're getting there. At least we know that now, big tech giants are getting a strong interest in that space because they see that now we have like efficiency that starts to be like super compatible with user experiences. But for many people, they still have in mind the state of the art of a few years back, like what it was in that space like 3 years ago, and where FHE was not ready for prime time. But the moment is like now-ish. Like there's been so much progress made on the crypto side of things, designing schemes that are inherently more efficient, and on the engineering side of things, doing homomorphic compilation, automated transformation of plain text programs into homomorphic programs, which we do at Zama, and other institutions, including private companies, also work in that space. But what is missing right now is, I would say, is adoption by the community of developers. I'm sure that business will come along, as soon as there is adoption in the developer community. So, and there is a lack of standardization. And as you know, as a company, you cannot take responsibility of investing in R&D efforts on a risky technology that is just emerging, so super exciting, but maybe you will invest a lot of efforts, and then in 2 years, a new standard will come up, and it will be like totally orthogonal to what you were doing. And so you have to reinvest efforts all over again. And so companies are usually, wait, or they do, POCs, like proof of concepts, prototypes. They can work on it a little bit to follow the state of the art. But what is really missing to, I would say, a global adoption of this technology is standardization. And as I was saying, also like open source tools that are easy to use, and so that anybody with a programming experience can actually produce and deploy easily homomorphic applications. So it sounds a little bit like a dream, but what we're building is precisely to go there. And we think that this is such a fantastic technology that it could change basically everything that we say currently about data privacy. And I have no doubt that there will be like consequences also in terms of regulations, in terms of data privacy laws. There will be an impact of this technology. But we believe it's like now-ish is the time for starting using this technology, And crypto can actually change the world. I mean, we've seen that for the blockchain and applications with cryptocurrencies and Ethereum and everything that emerged following this paradigm. And we think homomorphic encryption is one of these very powerful techniques by which you can actually change a lot of things in user experiences and change the face of the cloud.
Okay, thanks.
Thanks. So thank you for this fantastic.
Thank you for having me.
We'll close the session, and so let's go for a coffee outside and start the coffee break. Thanks.
Okay? It's my great pleasure to present you Laetitia Kameni, who is manager of IA in research and development at Accenture Labs. Her talk is about From Me to We, breaking down silos for new collaboration style. It's up to you.
Thank you very much, and hello everyone. I'm so pleased to be here today and to have the opportunity to share with you on some perspectives extracted from the Accenture 2021 Technology Vision Trends Report, which is a report that we have been doing on an annual basis for 21 years now. So before we get into the vision itself and the trends, let's first look back past month and year to set a bit the context. As you know, that period has been unbelievably dynamic and chaotic, and in particular because of the COVID-19. And actually, during that period, we felt, and even today, in some ways, we continue to feel a lot of uncertainty as change continues to accelerate in our lives. So when the pandemic hit, we experienced unprecedented disruptions, which showed the limitation of our established norms and the inflexibility of our work style, or even the fragility of supply chains. So from there, we have leaders and organizations which just ask themselves simple question: what do we do about that? How do we lead in such volatile world? And actually, how do we manage the unmanageable? So in the face of all these challenges, people and organizations just reinvent themselves naturally. So, and they actually used technology innovations to shape the new realities they were facing, breaking from past mindset, breaking for mode of living and working, old one, and taking new ways of interaction, adaptability, and even at personal level, get some kind of digital transformation. And actually, this is clearly different from anything we have ever experienced in the world. So it was very, very particular at that period. Then at this moment of truth, two things, I can say actually, two truths quickly became apparent. So firstly, one adage that you might maybe already heard about is that every business is a technology business. And the second thing is the fact that through technology, organizations can reshape industries and the human experience. So they start to have that possibility. But, and there is a but here, that happens only if those organizations learn to master change. And actually, that's why the most visionary leaders, those who use technology to actually master change, will be the one defining the future. And that is the overarching message from our Accenture vision this year, which is titled Leader Wanted, Experts at Change at a Moment of Truth. And in this report, in this study, we have identified 5 key trends that will shape the future. So the first is stack strategically. So this is about IT architecture becoming a crucial differentiator for businesses competing in the industries. And the second one, mirrored world, is about the power of massive intelligent data twins, AI, and data generating new possibilities for business and intelligence. The third one, I-Technologist, is about the democratization of technology. Here we say that if every business is a digital business, then every person needs to know technology and needs to be fluent in that technology. The fourth one, anywhere, everywhere, is about businesses taking advantage of the rise of remote and hybrid workplaces. And the last one, the fifth one, from we to we, is about a new take on partnerships and multi-party systems in the post-COVID-19 landscape. So I will now like to delve into this last trend, as it's related to collaboration, sharing, partnerships, and ecosystems. So here we see that the way business is conducted has evolved with the digital age. So we all feel that already. And companies use data analytics, the cloud, and mobility as technologies to share insights and services in ways that were previously unimaginable. So there have been a lot of progress in those domains. And those companies have actually invest a lot in those technologies. However, until recently, they had never really changed the way they partner. So most of the time, they are still operating in silos. And again, here, the pandemic revealed enterprise fragility as organizations were cut off from business partners and were just scrambling for answers. So that's what actually happened in the supply chain sector. Before COVID, many firms still relied on the physical paper trails, old and outdated processes, and often they worked with an established vendor or supplier because most of the time it was just much easier than onboarding someone new in their ecosystem. And with the crisis, of course, they find themselves locked down in a single partnership relation. And actually, that creates a lot of failures in the system. So, indeed, it's a little surprise that when the pandemic hit, 94% of Fortune 1000 businesses report supply chain disruptions. And 75% of them report that these disruptions negatively impact their business. So you can see how much the impact of this problematic have been for the enterprises. Then it's clear that companies can't navigate through disruption and uncertainty alone. And therefore, new ways of partnering are required. And there is now an imperative to build a resilient, adaptable, and trustworthy foundation for existing and future partnerships. So to achieve that, multi-party system will be required. They will be part of the solution, and as actually they represent this set of technologies which enable a shared data infrastructure between individuals and organizations, allowing to drive efficiency, build new business and revenue models. And in this set of technology, we have technology like blockchain, distributed ledger, distributed database, tokenization, and a variety of other technologies and capabilities like federated learning, which is actually one of the key topics we are discussing throughout this conference today. And actually, we start to see some companies and startups being very active in exploring and applying those technologies. So a couple of examples, even in my company. In Accenture Labs, we develop the concept of privacy-preserving data cooperatives, which is a framework that provides a standard interface between organizations willing to collaborate. And it allows companies to share data and collaborate without concern around trust, compliance, privacy, data control, or ownership. And it combines many technological techniques, such as confidential computing, homomorphic encryption. We heard a bit about it later. Multi-party computation and federated learning. Other example is the case of Edgify, which is a startup specialized in edge AI, which developed a collaborative framework to make the point of sales machine smarter and more accurate to enable low touch checkout experiences. And actually, they are also already thinking at applying this framework in other industries like medical, automotive, or manufacturing to identify spare parts, for example, in the industry. And another example, still in the industrial sector, is Bosch and Fetch AI, which combine AI and blockchain for predictive maintenance services. So the number of initiatives and cases is progressively growing, and we see a great dynamic, and at some point I'm sure that that will continue to take up. And we'll probably get additional example, in particular in healthcare, in the next session with our friend from Okin. So back on the ecosystem. So this ecosystem and strategic and shared platform that I talking about will not actually only help in the fight against future disruption, but they will also allow for ways to create new interactions or discover new ways to approach a market. And in fact, these partnerships will start to blur industries, boundaries, or even create really new industries. And we can look, for example, at BBVA, which is an international bank. So that bank had already developed a digital banking platform, but they wanted to reach new customers during the crisis. And to achieve this, they partner with Google, which is a tech giant, to develop a new banking product integrated with Google Pay. And in that way, the bank benefits from Google abilities to build great customer experiences, and in that way they saw an organic growth of their digital commerce services. And in the other hand, Google also took the opportunity to get, I would say, a foot in the financial sector industry. So to summarize, you can say that multi-party systems will help streamline inefficiencies and will be key to create those ecosystems. An organization will have to think strategically about how to work with others to build compelling new propositions. And we have already 90% of executives agree on that. But it's not just a matter of saying yes to the idea of an ecosystem, but also we need to ensure that systems are architected to allow the business and the ecosystem to reach their full potential. And to make it, there are three key things that an organization needs to consider. So first of all, make sure that it has the foundation needed to participate to an ecosystem economy. And here, the right basic equipment is the cloud. Secondly, it has to assess if this business is ready to participate in the multi-party systems, not only on the technological point of view, but also regarding other aspects around governance, the consortium rules and how to manage that consortiums. And the third is that they need to, the company needs to evaluate and anticipate the impact of its solution, if it's multi-party system solution, on existing strategic partner, but also on the individuals, as all the other societal change that could happen. So the technology, the change is not only a matter of technology, but also a matter of people. So we have to, and companies have to take all those aspects into account. Okay? So I will thank you here, and let me know if you have any question.
Thank you very much, Laetitia. So unfortunately, we are a little bit running out of time. Donc maybe we will delay the question, and I will propose that Mathieu Andreu now makes his talk about federated learning application in healthcare. Challenges and opportunities. Mathieu is a Federated Learning Group lead at Okin. So the stage is yours.
Hello. Thanks a lot, Christine, for the introduction. So I'll now show you some federated learning application of healthcare. My goal today is to convince you that healthcare is a nice setting to apply federated learning, and that there are lots of nice opportunities there, and also some interesting changes in terms of research. My talk will be organized as follows. I will first start with some motivating examples purely on the machine learning applications in healthcare, which are, I think, motivating for the use of federated learning, and then I will show some changes. Okay, so I will start with two motivational examples. The first one is an example of biomarker discovery with machine learning. This is a work that was done by Okin researchers and medical doctors 2 years ago. So this is a work on mesothelioma, which is a kind of cancer which is caused by asbestos, or amiante in French, which is something which is really used for isolation. And this cancer can be hard to predict its outcome. And so researchers and data scientists have trained a machine learning model which predicts the outcome of the disease given an image of the cancer at diagnosis. And the first good result is that this machine learning model was able to outperform the subtype and grade classification of the pathologist in its ability to separate patients among different risk scores. And this is already great in terms of machine learning, but this is not where the story ends in terms of medicine. Because this machine learning model was then designed to be interpretable, and in particular to point out which region of the image led to either to a high risk or low risk of cancer. And then, thanks to this interpretability, the data scientists were able to show the different subparts of the image to the researchers, which were either very high score or low risk. And by showing these tiles to researchers, they have been able to identify some specific patterns of the disease which were not known before, which were associated to lower survival. And this has led to a new subclassification of the disease. So here we have an example of using machine learning from data to synthesize new biomedical knowledge. Another example is H2RNA, which is a neural network which was trained on slides, so images of tissues, to predict the gene expression of the tumor. And so this machine learning model was then able to infer the genotype from phenotype information. That is just what is observable from the image. Further, this machine learning model was able to specialize it because the way the genomic information is computed is just, initially it was just for the whole slide, but it was able to retrieve it spatially. And this is really great because this virtual spatial information maybe help doctors in the future to allocate treatment to patients much more faster than now, because there is no need to undergo a next-gen sequencing of the tumor to know if the tumor will be receptive to immunotherapy. Just with a routine diagnosis, you can know it. And further, in the same fashion as I've shown before, it may be also possible to understand better this cancer and all different kinds of cancer. So these are examples of applications of machine learning in healthcare. So what I want to say is that machine learning opens the possibility to extract information from rich data, in particular from imaging modalities. And this information can be used to accelerate existing workflows by removing, for instance, the need to undergo next-gen sequencing, but also it can lead to the creation of new biomedical knowledge. So this is the motivation of why Hawking is interested in federated learning. Indeed, in order to train a machine learning model, you need to pool data to reach a critical mass. But data is sensitive, in particular for healthcare, there are privacy issues. Also, if you're talking about data that has been amassed by pharmaceutical companies, it is very competitive. There are also some cost and complexity of transferring data, and there are increasing regulations to monitor such transfers. And therefore, data remains in silos, which leads to a lack of diversity and representativity, because, for instance, if you have only data from a hospital in Nantes, then it has only seen patients from Nantes with its environmental factors, and it has not seen much more variability. And in some cases, for instance, for rare diseases, there is no center which shows enough data just to train a machine learning model. And this is where machine learning comes in. Machine learning, federated learning opens the possibility to perform collaboration without sharing data in a secure, compliant, and collaborative fashion. And to unlock federated learning, Hawking has started to build a data network of partner institutions with top researchers in each medical domain, with data from different modalities, including genomic, imaging, histopathology. And it's also building its own federated learning technology under the name Hawking Connect, which is able to connect these different centers to enable federated learning at scale. So this is the general picture. I will now show two examples of applications, of real-world applications of federated learning that are ongoing now. The first one is called Melody. This is a pilot project with 10 different pharmaceutical companies. The goal is to to train a model for drug discovery tasks. So each pharmaceutical company has amassed some data on on different chemical compounds, and they have done some assays measuring the chemical properties, and for instance the ways they bind to potential target. And this is really great, but each pharma may have focused on a different target area, and it would be great if we could pool all these data sets. However, we're really here in what we call the coopetitive framework, so it's we would like to collaborate among competitors. In particular, no pharmaceutical company wants the other pharmaceutical companies to know on which chemicals it has worked, because it represents a lot of sensitive information on where its next drugs are going to be. And this is really important in terms of its business strategy. And so here we are training a machine learning model with a multitask formulation. So there is a shared representation which is trained in a federated learning fashion, and then there is this is deep learning, and there are all the layers which are refined on each center. And real-world deployment is ongoing, and we may share results in the future. Another application that is going on is health chain, in particular for triple-negative breast cancer. So triple-negative breast cancer is kind of rare cancer affecting women mostly. And for this cancer, there is most patients mostly undergo, following diagnosis, a neoadjuvant chemotherapy just to reduce the size of the tumor, and then to undergo surgery to remove the tumor. And unfortunately, in some cases, patients have not responded to the chemotherapy and realize at surgery that response was either complete or not complete. And this is a pity because patients have to undergo a very toxic chemotherapy and they may not respond. And predicting this response is complicated even for very experienced doctors. And the goal of this project was to train a machine learning model to predict the response to chemotherapy from the diagnosis biopsy, so really the image of the cancer. And so we have set up a collaboration between Institut Curie and Centre Léon Bérard, where in each center you have images of the tumor and the histological response after the undergoing chemotherapy. And the goal is to predict. So this is a pilot project which is partly funded by BPI France, and there is real-world deployment ongoing also for this project. I'd like to point out that for this project, there are two changes. The first is that already it was not known before that machine learning could help for this task, and we're also carrying it out with federated learning because it's kind of a rare disease, and thanks to this, we're able to access a larger cohort. Okay, so these were some examples of what we do at Okin in terms of federated learning applications. Now I will present some challenges that we face in applying these technologies. So the first challenge is non-technical, and it's really important. We had a great talk previously on the legal aspects, and in fact, yes, data regulations are important. In particular, it's important that everybody agrees on the same understanding of the law, since it's quite new. And also, if you want to set up international collaborations, it's important to have a common framework. Another very important challenge is contracting, because there are lots of different stakeholders in making this kind of consortia. There is a hospital, within the hospital there are the doctors, the IT, then maybe you have a cloud provider, and maybe you have Okin, and maybe you have third parties. And you need everybody to agree on their roles, their responsibilities. In particular, you need to agree on value sharing, because the resulting consortium will lead to a machine learning model which may have a lot of value in itself. For instance, in the drug discovery example that I was showing before, the machine learning model may lead to finding better drugs in the future, so it has a lot of value. How do we split it? This is a question, and it needs to be solved and to be discussed and negotiated. Now, in terms of technical challenges, I think we've seen most of them already today, and I won't go into the details, but there is a challenge of privacy and confidentiality, because yes, data never leave centers with federated learning, but there are indirect exchanges of weights, of updates, and therefore there could be indirect privacy and confidentiality leaks. And I think that there's still a lot of work to be done to improve the privacy-utility trade-off in this direction. Another challenge that we face is simply to distribute some machine learning models. Because as we've seen today, the standard federated learning problem formulation is to minimize loss function, which is a sum of individual losses for each center, and typically the loss for a center is an empirical risk for given samples. And this is great, in particular for deep learning, it works great, but there are two hidden assumptions. The first is that the loss is separable across samples and centers, and also that parameters belong to a vector space, which makes it possible to perform gradient methods, and the notion of weight averaging makes sense. Now, what do you do when you want to train a machine learning model which does not respect these assumptions? For instance, the assumption of separability. In deep learning, what is really useful to get to a good performance is the batch normalization layer, but it's really non-separable. How do we do? There has been some work, especially last year, to try to understand what we do, what can be done, and typically it's just a layer which is left out and not federated. Another problem that we faced is that since we're interested in biomedical applications, we use a lot of survival analysis and this model called Cox proportional hazard. And when you look at the loss function, it's also non-separable. And what do you do in this case? Do you make proxies for the loss, or do you try still to compute the full loss? It's not trivial. And a last question, and really open, is how do you do when the parameters do not belong to a vector space, in particular for tree-based models, which are getting the best performance, in particular when you're using tabular data? This is a challenge that we face. The last challenge that we face is data heterogeneity. These are examples of images that were really created at different hospitals, and due to the varying chemical compounds that were used to stain the slides, it led to slightly different colors. You really see it when you look at the histogram. And this is just for the visible part. But in fact, you can have much more factors of variability, such as demographics, the techniques that were used to prepare the data, and the way the cohort was built, because we're using retrospective cohorts, and they may have been for some purposes. And this, as we've seen today, this can lead to a lot of issues. It can lead to statistical biases. So the question is, how do we formalize this heterogeneity? We've seen some answers today. Because heterogeneity is way too large, we need to define subtypes of heterogeneity and define adaptive methods for each subtype. And ideally, we need to find methods to automatically detect and adjust to these settings so as to be able to work in the federated learning setting. And the last challenge is to integrate all constraints, because we have the privacy constraint, we have the heterogeneity constraint, for instance. And if you have a lot of heterogeneity, maybe you want to communicate much more often, for instance. But then, is it compatible with your privacy budget? And if you want to distribute some fancy machine learning model, you set up a novel algorithm to do so. Is it private? And this is, I think, what federated learning is about. It's about integrating all these constraints into a single thing that works. So to conclude, I think machine learning has a lot of opportunities to accelerate medical research, and federated learning is a great tool to break silos and to enable collaborations. And this setting in particular of healthcare presents a lot of exciting challenges and research topics. Thanks for your attention.
So, thank you very much, Mathieu, for your talk. We have 2 minutes for maybe 1 or 2 questions, either for Mathieu or for Laetitia. No? Ah, okay.
If I really understand it right from you, Hawking value added is the ability to gather a large number of data from competitors who would dare to share it for its treatment with the basis of an independent, confidential intermediary. That means you can get the data, you can treat it properly with professional skills, and restitute to the owner without the danger that this data sharing would be falling, the origin of the data would be falling on the end of a competitor. You are a kind of SAS to speak about a submarine, and this is where the need for you to exist is a very strong value for the economy. Is it right?
So we're not sharing data. We really, data stays where it was, either in the pharmaceutical centers or in the hospitals, and we simply access it to train a machine learning model, and only the model itself sees the data.
To speak about the preceding one, the lady, actually what was a very strong value about what he explained is that the new economical model that would be needed for the future would be model in which each new brick to add value, to add expertise, competence, would be remunerated, would be paid on a fair value. And according to that, the question to mislead, please, would be, please, according to you, in this economic model of fair value for each participants of value creation, would need, including the consulting firms, the people who provide strategical advice, would be part of this revenue sharing model where they would be remunerated according to the value they bring to their client's company. That means McKinsey, Boston Consulting Group, your company would in the future be paid not as providing means, but as results, as a share, a fair share of the value they provide.
Thank you for your question. So the point that you mentioned is very important indeed, because you are talking here about how in an ecosystem, in a shared economy, actually, every participant is getting benefits of actually either providing services in that one. So I will say that usually when a party or company or an individual participate in an ecosystem, that's most of the time, of course, because he finds his interest. So, and the companies that some of those that you mentioned there, which are kind of providing technology, also have their role to play in that shared. So they provide the technology, which is something that is actually not possible for, any individuals to create. So those companies provide the platform. So this is one thing also variable for all. And people, then individuals, are using those platforms to share services, to exchange services and value. And the fact that the revenues are not all the time equally shared is just a matter of how the ecosystem, the governance of the ecosystem. And this is something that will tend, of course, to be balanced. And I think that as every individual will have the opportunity to participate or to not participate to an ecosystem, we also let him the chance to kind of evaluate the return on investment that it gets from that ecosystem. Thank you.
Okay, so I thank you to. I propose to thank you our both speakers, and now it's time for the panel, industrial panel.
Okay, so we are now going to have the industrial panel. The goal of this panel is basically to reflect on what we've seen during the day and to discuss some of the directions and challenges with 4 experts of the domain. So I'm first going to introduce everyone, starting from the right. So Aurélien, we have seen Aurélien earlier today. For those who are not around, Aurélien is a researcher. He's working at INRIA in Lille, and he's an expert on privacy-preserving machine learning. So he gave a talk about those topics. Then Mev, so Mev Corcoran, hope I pronounced that correctly, is managing director at Accenture Labs. So she drives the artificial intelligence R&D work, and she focuses on responsible AI, on how to organize the global response AI lead for technology innovation. So one of the topics that you are an expert on is algorithmic fairness, and we are going to discuss that during this panel. Then Bruno. Bruno is CTO and co-founder of Cosmian. Cosmian aims at applying and expanding the use of encryption, so what was described in the second talk of the afternoon. And the goal is to, basically enable companies to use, to leverage encryption techniques in machine learning. And finally, Victor. So Victor works in the same company as Mathieu, who just presented. In Okin, you are head of commercial operations, and basically you are responsible for the commercial development of Okin, Federated Learning Platform for medical application. And so I would first like to thank all our speakers for being present today and for participating in this panel. And just for those who don't know me, I'm Emeric Delveux, and I'm just assistant professor at Polytechnic, so that I don't remain anonymous. Okay, so we just have 1 hour, and I hope we have time for questions of the audience at the end. But I would like first to, basically we are going to try to organize the discussions in 3 main parts. We would like first to discuss about federated learning at large, and all the things we have seen today. Then we would like to talk about privacy, because many of our panelists are experts on the privacy topic. And finally, we would like to go beyond what we have discussed, possibly discuss about fairness and ethics and other things that possibly are not at the heart of federated learning, but are still extremely important on many aspects. So, I would like to thank to Mathieu and Laetitia that gave us a perfect introduction to the challenges of federated learning, and obviously all the speakers. And I would like to start by a very simple question, perhaps to Victor and Mev, about the use cases that you have and the challenges that are the most possibly important or hardest to tackle. Mathieu just presented that. There is privacy constraints, there is engaging people, there is scale issues, etc. What are the most important aspects? In some of the cases, perhaps you had just described one example and describe what the challenges are. So you have a mic here.
Okay, I'll go first. Is it on? Yeah. So I suppose in terms of sort of the use case at the moment where we're seeing the most potential, I think a lot in the healthcare and life sciences space, and that was sort of evident today with a lot of the examples in the research were around that space. Also some examples in, say, financial services where the federated learning happens within the same country, say across country borders. So they're sort of the main spaces in terms of where the key constraints are at the moment. I think from a technical side of things, there is obviously the side of privacy and security. So again, a lot of the research we saw was in that space. Also, unbalanced data sets, and then also the whole side of communication. So they're all sort of being tackled by researchers at the moment, which is great. I think from a business side of things then, in terms of big constraints, what we're seeing is things like, well, the key one that I've seen in where I've worked with clients is actually on the liability side. So there's a lot of talk today about privacy guarantees, but as soon as you start talking to a company about privacy guarantees, they say, oh great, you're guaranteeing privacy, therefore if there's any data breach, you'll be liable for it. And we're like, oh, no. And then they say, well, then it's not a privacy guarantee. So I think that actually that is a really key element, especially when there's personal data involved from a business point of view. And then the other thing from a business point of view is value, proving out value. So there's a lot of theoretical value out there and over the last number of years, and there's loads of money going into startups, you know, to get to value, but there isn't that many examples yet of proved value, and I think the more of those that we have, the easier it will be to get business along.
Thanks. So I'm not necessarily going to repeat all the challenges that Mathieu, you know, very well highlighted, but perhaps taking on an example of some of the applications of federated learning at Alkin. So in the Melody consortium, where we have 10 competitors who are working together using very, very sensitive and private data. And then on the health chain side, where we have 2 hospitals collaborating with Alkin on very sensitive, but in this case, you know, personally identifiable data. One of the common challenges that we see across all federated learning projects is, first of all, that each one of them is very unique. And so the partners that come together to put together a federated learning project have their own perception of risk, have their own perception of what they want to protect, and therefore where they want to focus all of their efforts in terms of protecting the privacy of their data, the confidentiality of the data, the model. And so it's a real discussion, and it's a real kind of tailoring every time of setting up a network for these partners. And I would say the other challenge, and again, on top of what Mathieu said, and data heterogeneity and privacy, is one of leadership. And by that I mean that a lot of these consortia are formed because one person or 2 institutions who you know each other and work together, you know, really take the leadership on forming that consortium and say, we're going to be using these technologies, we're going to be setting up a federated learning consortium, and therefore we need to take some of that responsibility. And that leadership actually carries a lot of effort, because you have to convince other people. And so if you think about the Melody consortium, you have here 10 experts in drug discovery coming together, led originally by somebody at Janssen and Novartis, really pulling this group of peers together and saying, we're going to try something that's very cutting edge, that's transformative. And everybody kind of needs to take a leap of faith. And to do that, everybody needs to follow, you know, somebody's leadership. And I think that's the other, you know, difficult and hidden angle of a lot of these federated learning projects today, is that it requires the corralling of a group of people. And that means then convincing legal departments. And so imagine convincing 10 pharmaceutical companies' legal departments to share some of their most sensitive data. And in fact, they're not sharing it, but, you know, to register it into the network. Again, that requires leadership internally and some champions internally at those companies. And same thing, if you think about health chain and the hospitals, you need the professors to take on that champion role internally at the hospital and convince the IT departments and the legal departments that, yes, we're going to participate in this, and to really tackle each roadblock as they come along, because it's an educational challenge for all of these departments. So I think that there's been a lot of technical challenges highlighted, but there's also a big, you know, people component to this that we need to acknowledge and work through.
So thank you very much. This is very interesting. And on that point, on the how to engage people to participate in the federated learning process. So in your experiments, do people come to you with asking how it can be done, or do you have to convince people? And if you have to convince people, what are the best ways to do so? I don't know. Perhaps Bruno, in your experiment, perhaps.
Well, we usually don't go to people; they come to us. It's already hard enough to convince people to do stuff with brand new technology. So if you start evangelizing those technologies, you just make it much harder for adoption. So we usually, what we really like is to tackle challenges where there is no other solution. So we are not a substitute to something that works or more or less works, but where there is no other solution than enabling technologies such as differential privacy or cryptography to be able to tackle the issue. If you don't do this, immediately people will start to compare, you know, what happens if I do this in clear text or in a normal way compared to your way. And obviously doing differential privacy has a cost. You add noise. You're doing cryptography, you have a cost, performance or ciphertext size. So there is a cost of doing this. So I think at the moment, what the market is ripe for is really projects where there is no other solution. Really, you're not a substitute to something that exists, but you enable these kind of technologies where that's the only way to move forward. And finding these use cases is not that easy, actually.
Okay, that's very interesting. So does someone else want to react on that? How to engage people, perhaps?
Yeah, Maybe just a quick word. I think again, we're working with often perhaps early technology adopters, but there's still a massive learning curve, and so pilot projects and getting simple examples through the door and getting people familiar with the technology is a great way to obviously get that adoption going, and that can come from either people coming to you with the problem that they've identified, or sometimes for people who are very knowledgeable about the industry, and again at Auken we have very specific knowledge around histopathology in the case of oncology, coming to companies and saying, hey, we have identified this problem and we think this technology can help you. Is that a problem that you feel acutely? And then you start building a relationship with your clients and you start to look at applying that technology. But I think the other side also is to try and make sure that your customers, the people on the other side, are understanding what they get out of this. So in the case of Melody, for example, each pharmaceutical partner that participates in this network walks away with a model that is unique to them. So it's a setup that we commonly kind of label vertically partitioned federated learning, where each participant comes to the game with their own data, but everybody walks away also with a model that is unique to them. It's been trained and it's seen common data, and it's seen the data from the 9 others, but it's something that belongs to them. So you're not compromising intellectual property for them. You're not leveling the playing field and saying everybody's going to now use the same drug discovery model. It's now something that everybody retains in a unique setting. So the key in kind of overcoming, I think, some of these objections and overcoming and getting people engaged is really detailing, what's going to be in it for them to participate in a game where others might benefit from their data or the hard work that they've put in over all these years.
Thank you. Aurélien, do you want to say a word on that? Or?
Maybe more of a comment is that also sometimes you get surprises, maybe in what convinces people in a particular use case. So I'm also working a bit in a project for Federated with hospitals. And so maybe you guys have had a similar experience, but for example, one of the arguments that convinced the physicians the best was the fact that it's potentially much lighter to update a study when you get a little bit more data than you were, because currently the processes that they have for doing these multi-centric studies across different hospitals are very, very heavy. And so they are not going to go through that again if they have a bit more data. And so they were kind of quite convinced by this argument, which was obviously not the one that we had come up first to try to convince them. So yeah, it's important to understand the needs, I guess, in each of these use cases.
Thank you. Okay, so I think another point we could mention is, I think there are many researchers in the room. So who is doing research in the room, just to double check? Yeah, that's about half of the people. And I'd like to ask to people in industry, so there is clearly today kind of a gap between what we are doing in research and what happens in industry, because I mean, we're sometimes tackling problems that are perhaps a bit too advanced or not necessarily corresponding to the challenges that you face in practice in order to, I mean, have the methods in place and just engage people. And I would like to ask to people in industry what they think the biggest challenge is yet for us in research. So what are the directions in which we do not have yet a proper answer, and what are the directions we should tackle? And I'm going to ask the question first to people in industry, and then perhaps to Aurélien what he thinks the biggest challenges are for us in the next few years. So yeah, I don't know, who wants to react? Perhaps Mev, if you want.
I think in terms of, and we saw it here today, I think in terms of academia, it's really important that there's a mix of projects in academia, some that are tackling the really hard problems that will take more than a year to tackle, that might take the length of a PhD to tackle, but then also that there's sort of some of it that is actually staying closer to industry and looking to see, okay, with what's actually there now or applying something over here, can you actually solve a problem for industry in the next 6 to 12 months. So I think, but it was really good to see today. There was a really nice mix of projects as well here, in terms of some were actually direct collaborations with industry where they were trying to solve an industry problem, and then others were a little bit deeper and going further along. So I think that's really important from an industry point of view, and from a research point of view, that there's a balance there. Like harping back to the privacy thing, I think that's an area where I don't think academic research on its own is going to solve it for, in terms of what I was talking about, liability and stuff, but actually the more we can solve, because interesting when we were talking earlier, you were saying, oh, there's all these different avenues that we can still explore. Like for industry, they need all of those to be closed down and to be clear. So there's still a good bit to do there. So I think that's one of the areas where if academia can keep going and then industry looks for other interesting ways to maybe help solve it. Like I think, was it you were saying earlier, maybe it's a new area for insurance. They could decide to insure the risk of data breach when federated learning is used. So, but they'll need a confidence as well. So I think it'll be a balance between industry and academia to solve some of the problems.
I just wanted to say researchers are doing a great job. They are actually going faster than the industry. When you look at advances in cryptography, I think Pascal has been giving you FHE, but FHE is not the only cryptographic mechanism out there. There is MPC, there is FE, there are many, and they're all moving extremely fast. Same thing on the differential privacy side, sorry. What's really missing today, I think, for mass adoption is that we're not talking about adding privacy, but that it becomes privacy by default, not by design, but by default. So when you get a piece of software in your company, you don't have to worry about what sort of encryption it is using or whether there is differential privacy in there. It must just be in there. And we are clearly not at this stage today. So I think the next, to me, the next challenge is really how we can bring these technologies to something which is usable and injectable, become a ground technology that becomes part of any software design basically that we do. So a standard developer, when he enables a database or an application server, doesn't have to worry about whether cryptography is in there or not. It's in there, it just works. He wants to do an homomorphic addition, fine, it's in there. He just has to call something and it's just in there. We are not there yet. So I think a lot of research has to go into, and Pascal was mentioning on this, and you know, normalizing things, making things available. So it takes a little bit of time, but researchers are doing a great job. They are moving extremely fast on all these fronts.
Maybe from my perspective, and maybe there's more of a commercial one, but is to say, to create more consortia and to have more international collaborations and to have, especially in the medical field, to have more researchers say, actually, I want to collaborate with so-and-so from this institute and I want to combine our data, and so I want to see what we can do by joining our data sets, create more use cases for federated learning and for the types of encryption technologies that are being developed, so that it's going to drive and continue to drive then the need to actually develop and deploy those technologies. So more kind of on the application side, continue to drive those applications. All of these IMI consortia are fantastic. These EU consortia are fantastic because they're really driving that, but they don't necessarily need to happen under these massive frameworks. They can also happen between just two researchers who really appreciate working together, but one is based in France, the other one is based in Japan, and they just cannot combine their data. Well, here we have a use case, so more of those.
Aurélien, so to ask the question, Aurélien, what's the direction you are the most excited about, and one challenge that you think is completely locked for the moment, or something that is big to unlock?
Yeah, so of course this is kind of difficult to look ahead in this field because it's a very active one, but maybe things connected to research, but also I think which can have a very important impact in practice. I think one of these things is to kind of generalize the idea of federated learning to encompass essentially data science, the whole data science pipeline, which, okay, machine learning is one component when you do data science, but you also need to do other things. First, you need to do data exploration, okay, and then when you train, you need to tune hyperparameters, and there's many things that you need to do, and I guess looking ahead, it would be very nice to be able to do this whole pipeline without having access to the data, right? And so kind of adapting the tools, adapting the algorithms to make them usable in this fashion. For normal data scientists, so to speak, that don't have specific expertise, maybe in federated learning, to be able to use those tools. And then when you add privacy on top of that, there is something that is very important and I think needs a lot more work, is automatic privacy accounting. So this is the idea that, you know, there is someone that wants to compute things on the data, and it's typically a sequence of operations that are adaptive. So when you do data science, you first look at the data or get information about the data, and then based on that, you choose the next thing to do and so on, right? And we need to be able, if we have privacy guarantees, for example, differential privacy guarantees, to be able to tightly keep track of that budget. And so I think there is still a lot to do there. We have like the basic principles of that, like this composition idea, right, from differential privacy, addresses that to some extent, but it's often quite loose, and there are many ways that when you know a bit more about the operations that you are doing, that you can optimize this process. And so I think this also will have a lot of impact. And then maybe one last thing, which is dear to my heart, is kind of also bringing these tools to kind of the citizen level. So right now, the big promoters of federated learning are, in the end, mostly maybe remains Google, who even invented the thing. And so this is great, right? This is probably an improvement that Google can do whatever it's doing without really having the data locally. But in the end, normal people do not really have access to the fact of training these models and getting this insight and so on. And so I think there are nice challenges also for software, hardware, so that citizens can actually get in control and decide also for themselves, okay, let's all, you know, go and compute this thing or learn a model to do that. And yes, empower people in this way. So I think that's a very exciting challenge.
We have a lot of work to do. Okay.
And we'll need politics also.
Yeah. So who wants to do politics here? Okay. Okay, so I think that the privacy point is one point that somehow binds all of you together. So we have seen a couple of very interesting presentations. You talked a lot about DP and a bit of encryption. Pascal obviously talked about encryption. I think that's something that can be used together. I would first like to ask to Victor and Bruno which technologies you use. Perhaps Bruno, you can give a bit of some elements on what exactly your company does first.
Okay, yeah, we, as Cosmian, we actually build enterprise software, so something that can be used in IT in large companies that includes encryption techniques precisely when you want to protect data or protect a model, or you want to give privacy to the users behind the data. So we're bringing really the advanced encryption techniques and some differential privacy too as well now into enterprise software, because we think this is the only way to make it mainstream, is that IT people can just get the software with that inside. So that's what we do. That's our mission, is to bring this research into IT software. Now, today the scope is very wide. So you have, I would say, clear text techniques like differential privacy that adds noise, for instance, to clear text, to, let's say, more cryptographic techniques. And cryptographic techniques, you have many, even homomorphic cryptographic techniques, there are many. We've seen FHE, which is probably one of the most exciting, actually, for the mathematicians, it definitely is. It's a fantastic toolbox. But there are other techniques like multi-party computation, functional encryption, in which the lab here at ENS is probably one of the most advanced in the world. There are even hardware techniques like secure enclaves, TEs, notably Intel SGX or AMD SEV. So basically you have processors comes with secrets inside the processors. And all these techniques have different security parameters when you look at it. They can have formal security subparameters like in FHE, so we can do math and prove that what we do is correct. They can be they just work, like some symmetric systems, or well, you hope they work like trusted enclaves and nobody can break them because they're subject to side channel attacks. So you have different security parameters, and also these techniques usually have different impact on your data and the performance. FHE will tend to be less performant sometimes with other techniques in terms of CPU, and will tend to have a higher expansion, a bigger expansion of clear text data to the size of ciphertext. Ciphertext will tend to be big. Other techniques like MPC don't have this. However, they have a lot of communication rounds. So depending on your setting, usually, who you work with, what you want to achieve, usually is the main factor in choosing which technology you're going to enable. Do you want performance? Can you have good communication between partners or not? Do you need to minimize interactions? All these aspects, what sort of calculations you want to run. If we want to do linear operations, functional encryption is super efficient. Usually the external factors is what is going to drive the sort of technologies you're going to use, and sometimes we do a combination of technologies actually. So there is no good single response to what should I do to protect privacy technically. It will really depend on your setting and the sort of computation that you will want to achieve.
Thank you very much. And Victor, so perhaps
Yeah,
can you...
I think you've actually said it all. It's that it's extremely custom and it's extremely dependent on the setting and the parameters that you're trying to optimize for. And in the case of, for example, Melody, actually they're using secure aggregation as a way to protect the model updates and minimize the risk of inference attacks on any single server. But that technique may not be the right one for a company who wants to train their model on medical images from different centers. And so again, we have to adapt to the individual needs of the consortia of the network.
Okay, and yeah, perhaps on the Aurélien and a point on how to combine possibly both approach.
Yes, so of course these techniques can address different privacy or security problems, but they can also be combined to provide maybe better solutions or different trade-offs for a given problem. So for instance, some of the work that I presented, the first part, is a case where allowing to use secure channels, which is essentially based on public key encryption most of the time, allows you to improve the privacy UTG trade-off of differential privacy. Conversely, there is a whole line of work where people want to use MPC, so multi-party secure computation, but sometimes that is expensive, and so you can relax a bit the model and say, okay, I'm not going to reveal only the output, but maybe I will reveal a bit of intermediate results, but I will protect them with DP. And in this way, you leak a bit more than pure MPC, but you can hope to improve a lot the computational efficiency, for instance. So there are a lot of things like that. This is true also for enclaves. So like you mentioned, enclaves, they have these site channel leakage sometimes. Maybe if you observe communication or if you observe memory accesses, this leaks information, and GP, for instance, in some cases can be used to mitigate these leakages. And so, yes, I think the value lies in most cases in also combining these solutions.
Yeah, no, just to agree. What we're seeing is usually occasionally it's one, but usually it's more than one of the techniques that's applied for use case.
Sure. And I mean, following on that, perhaps a kind of a provocative question. I mean, do you believe that we have a good enough understanding to just, I mean, really push for those methods and to, I mean, develop them and really ask people to trust everything that we do? Or, I mean, when we see DP, we know that, I mean, there is a lot of a huge high importance on the parameters. We've heard, or at least I've heard that, I mean, the way the industry choose those parameters is not always satisfying. I mean, we are advertising for a technique, I mean, we are communicating to the public and pushing for these kind of techniques. Do we believe that we have, I mean, enough, just like good enough understanding of those techniques, or shall we be a bit careful on that? Maeve, go ahead.
I think, like I think, and it was mentioned, you were saying about how it's hard to find the right use case at the moment. I think there are use cases today with what we know today and what we're confident about today, where you can get to value in the use cases. So I think for me, there's sort of two parallel streams. It's working with industry to find those use cases and get them implemented and get to value, because also you learn a lot as you get to value, even in small use cases. And then in parallel, keep improving through research. And then hopefully in a few years' time, they'll meet together and it'll be possible for federated learning at scale for everyone and for the common user as well then.
Okay, and perhaps, I mean, at some point, do you believe that companies like Accenture or Hawkin will be able to assume the liability to, I mean, somehow guarantee that there is no loss of privacy and not rely on some, I mean, I think you mentioned earlier that perhaps one day there would be insurance to insure the loss of privacy. But, I mean, if we really believe in the technique, when are we going to be able to, I mean, just guarantee it without relying on some external party?
But I think the thing is, the risk is never going to be zero. You know, realistically, it's never going to be zero. So I think it's much more likely to bring in a third party that actually their business is to ensure risk that you can't guarantee, that, you know, that someone like Accenture can't guarantee against. So I think that's probably the more likely way to resolve this in the shorter term.
Yes, thank you very much. Do you know if does anyone know if there exists such a project to ensure the loss of privacy? Okay, anyone in the room? I mean, so you can also react if at some point someone...
The usual way is you go through certification at some stage. So basically, you have standard practices. So first, I want to say, industry behave is a bit, you know, a bit like sheep. I have to. If one does it and it works, all the other guys are going to do it. So usually, in one single industry, you know who is the early adopter. You know, among banks, you know, these banks usually are the guys who try stuff. You know. Like a bit like Israel with COVID, you know. Usually you can single out per industry the guys who actually try the new stuff. So everybody's watching them, and if it works for them, the other guys do it. Now, in terms of and we need these use cases, we need these successes, and that's what we are looking for right now. I think for all these techniques, just to make them mainstream. Then what's really going to make mainstream and solve, I think, a lot of the legal issues. Also, the legal frameworks are new. GDPR is new, so and we understood from the presentation it's not exactly clear-cut exactly what you can do or not do, unless I guess you get a lawyer or multiple lawyers, but it's not exactly clear-cut. So a way of solving this is through certification. So you will have organisms like NIST for cryptography. I'm talking my shop, but it exists everywhere, like NIST or ANSI in France, who are going to start certifying technical things, certifying certain crypto. Now, clearly they lag usually very much what we can do in research. So today we are doing homomorphic encryption with quantum resistant paradigms, encryption systems, and they are still looking at elliptic curve right now certification. So that's where we are. So NIST is at the moment starting to certify the first quantum-resistant cryptographic primitives, but only for a very specific case, which is to use in HTTPS for the TLS connection. So, you know, certification takes a lot of time, but it will come. It's moving forward. And once you have certification, then I think the legal aspects will sort of solve by themselves, because as a company, you will be able to say, well, look, I use the certified stuff, and I can prove by the logs that I did things correctly, and then liability will become less of an issue or more a common issue.
Okay, and go ahead.
Maybe on the point of certifying or underwriting the risk. So, well, Oaken's business is not to underwrite any risks, to develop the software. But I believe that there will always be people who are willing to get paid a premium to take on some of the risk. But in the case of federated learning, clearly these companies, whether they're insurance companies or kind of a new generation of insurance companies, are going to have to be very technically minded. They're going to have to be able to dive into the technical detail of your solution and test them most likely. And so that's going to require a massive learning curve for these companies and a huge expertise internally that we're all fighting for, because we all want those experts internally to our companies. So I think that's also going to take quite some time before the industry is ready to kind of underwrite that risk. And so until then, each participant in these federated learning networks have to accept some level of risk, have to accept some level of liability. And today most companies anyway all companies should have insurance, and they all have insurance on to protect them on GDPR breaches and stuff like that as well. So there is already a framework by which companies can kind of feel some kind of, okay, we have de-risked this and we have sort of insured this to some extent. But when you're then setting up a federated learning network, if there's somebody ready to underwrite that and kind of underwrite it as part of their commercial value proposition, I think we're not quite there yet in terms of where the technical kind of knowledge of the industry is at to be able to provide that kind of service. But I think it'd be a very, very interesting and promising future once they're there.
Yeah, thank you. And regarding how to set the DP parameters, perhaps Aurélien, do you know how it's done in practice? Do you have examples, or anyone working with DP, how do you choose basically those parameters?
Yeah, so this is a tough question. So, and maybe I have a bad example of that. But first of all, okay, so in relation to this, maybe for trust, you need also some kind of transparency about this, because of course, for differential privacy, at least, saying we protect data or whatever with differential privacy doesn't really mean anything, right? I can take epsilon equal 10,000 and then probably, this is differentially private, but with parameters that are not protecting anything. So some level of transparency, I think, is needed there. When it's possible that the code itself is available, this is best. So of course, it's not always possible, especially in the business scenarios. But at least being kind of transparent about maybe the parameters that are used is important. And so, for example, a bad example of that was a system that Apple deployed at some point, right, where they deployed differential privacy without really being very clear how they implemented it, what was the budget, and so on. And so some researchers reversed engineer their system in a pretty smart way, and so they showed that the budget was above 10 for epsilon, I think, and they were also resetting it every day for any given user. So basically, right? So this is more like probably privacy washing than privacy. Okay, it remains a tough question though in practice for a given use case. I think what parameters are, the good choice to get some privacy protection, but also not ruin completely the utility. But there has been quite some works now for the past maybe couple of years on evaluating this, I think, with attacks like these membership inference attacks and so on. So I think there is a lot of progress made there, which gives some way to kind of try to translate for a given use case. So it's hard to generalize across use cases, but at least there are empirical ways to evaluate a bit, translate an epsilon, for instance, of differential privacy into a concrete kind of protection in terms of data reconstruction or membership inference and so on. But this is a tough question in general, I think.
We had an example where we were actually, it was around synthetic data generation, but again, it was to show that it was different enough from the seed data, which is the real data, to be able to leave the organization. So we were looking at privacy, and actually, so it was setting the parameters, but then as well for the client, it was showing them, okay, for this parameter, because they had the same question, how do I even know if that's a good parameter? And we explained the maths, and they got it. It was data scientists, but then it was, okay, we've set this boundary just above this boundary, so the ones that we're saying are not private enough, so we're going to delete them out of the data set. We'll show you the top 50 of those, and so, like pairs, here's one of them, and here's what's most close to it, and they could look at it with their business experience and say, okay, yeah, there's no way you're going to, that's very different to that, you can't, or no, they're too close, and then you say, okay, well, the value then is wrong, we need to make it more private. So being able to have some method for the end user to visually see what it means rather than just a mathematical formula is really important as well.
Sorry, maybe just to give also another concrete example. So I mentioned in the talk that the US Census started implementing differential privacy. So US Census is like the equivalent of INSEE in France, right? So in the US, they publish statistics, and so they have now implemented differential privacy, so they don't release exact statistics anymore. And to do that, of course, they had to face this problem. Okay, how do I set epsilon for this and these statistics? And the way they did that is really by doing these empirical studies on historical data. So, okay, they are the US Census, so they've been releasing data in the clear for a long time. And so it was kind of, in their case, not easy, but at least they had the data to evaluate on past data what parameters may make sense. And there is a lawsuit, actually, right now in the US, of people complaining that this is ruining the statistics and so on. So this is a quite interesting lawsuit to follow.
So the lawsuit is complaining that they added too much privacy, or too much noise.
They are saying that this is all not necessary, that the attacks that people show are kind of unrealistic and stuff. And I think the arguments are mostly flawed, at least from a scientific point of view. So yes, this thing is ongoing, and a lot of DP experts have kind of entered also a bit the debate. So it's quite I think quite interesting to follow.
Okay, thank you very much. Any other reaction on that? So otherwise, I mean, I think there is another point that was the topic of many questions today is data valuation and how do you share the profits. I think it's clear that has been a very complicated question, but just you were presenting the pharmaceutical example. How do you at least ensure that one of the participants is just not, participating without any data? And how did you deal with the fact that, someone could just be here to gain a model without bringing anything to the table?
Yeah, so a really interesting question, and I think there are multiple layers to it. There's a technical layer, so you can implement, technical safeguards to check if somebody submitted the same data over and over and over again, and so you're having, you're just optimizing millions of times on the same task. Or you can also perhaps say, okay, well, we have a model that's also seen public data, and so can we check whether or not the participant has uploaded public data instead of their own private one? So there are technical solutions, but if there are technical solutions, there will always be technical people who outsmart you. And so then there's also a people layer. So of course you've got the contractual layer, but you've got a people layer. And I think that's important to consider is that, again, if you have a consortium like Melody, or if you have a consortium where 10 peers who are, you know, industry leads in their field come together and work together in a collaborative but competitive, so a competitive environment, you have a kind of, well, you have a game that's set up, right? And so you have a system in which you want everybody to be playing the game, and if one person is not playing the game, how does that impact their relationship with the 9 other players in an industry where you know, everybody kind of knows each other, and B, your career and your name is at stake as well. So I think there is that kind of people layer that's not to be underestimated, and you can lean on that and ensure that every participant plays the game in a way that's fair, of course, for all the other participants, but also that you know, that they've got something to lose if they don't play the game. And so we can show also that they've got something to lose if they don't play the game technically, that they're not going to benefit as much, but you can also show that they've got perhaps something else and bigger to lose if they're not playing the game as a participant in this network of 10 people. So that's why, and again, you know, this might be very particular to the types of federated learning consortia that we build at Aukin, but again, for me, you're bringing people together. So we're not talking about a federated learning consortium of, you know, 10 million devices and it's completely anonymous. We're bringing together 5 hospitals or 7 pharmaceutical companies or 3 hospitals and 2 companies. And so there are individual project leads at each of these institutions that come together, and that adds this layer, which I think, you know, for me, can really be used to safeguard and to help ensure that everybody plays the game in a way that benefits them and benefits the whole consortium.
And just to follow up on that, so at the end of you said that each company got its own model. So was, I mean, the model just somehow personalized, or was the quality of the model, I mean, depending on how much they brought, or, I mean, was that even a question you considered?
Yeah, so there's a lot of information you can get on the website, which is melody.eu, and melody spelled with 2 Ds. So, but there are a couple different things here. So it's quite a unique environment because everybody brings to the game their own components, and nobody ahead of the time agrees on what data they're going to bring. So you saw the graph that kind of Mathieu showed about compounds and assays. There's no coordination between the partners ahead of time that we're going to bring these compounds and we're going to bring these assays, and therefore we're going to optimize for these tasks. So you're kind of, the model goes in, you know, effectively blind, and so it has to be prepared to learn on any combination of compounds and molecules. So if you think about a picnic, for example, everybody comes to the picnic with their own food, and nobody coordinates whether, you know, this person's bringing starters and just cucumbers, and this person is bringing just, you know, starters as well, and everybody just ends up eating starters, or if you've actually got a complete meal. Whereas in the case of health chain, if we take the picnic analogy again, we've optimized already ahead of time, and we know what we're bringing to the table, so we know that everybody's going to be eating the same kind of complete meal at the end of the day. And so the way that it's been set up in Melody is that, okay, so you've got this first layer of complexity where you don't know kind of what people are bringing to the table, and the second split has been done that you've got a common trunk model that is what's been kind of trained on every data that's been registered, and then there's the optimization tasks that happen on each individual server on each individual's data. So they're walking away with a model that's unique to theirs, that's been optimized to their data, but that has seen and that has been trained on a common set of registered data. And so again, from that perspective, you're enabling people to come, again, to use the picnic analogy, to the picnic with whatever they decide to bring, but also to walk away with their own choice of what they've decided to eat, and effectively, you know, walk away with their own full stomach, if you will. Whereas in the health chain project, where everybody's walking away having eaten the same thing and having, you know, brought and coordinated, decide what they would bring. So the analogy is a bit stretched, but I think it helps to exemplify kind of the 2 different setups that you can have. And so the first one is vertically partitioned, and the second one would be called horizontally partitioned. Yeah.
Thank you very much. So
Can I ask one more question? So on the Melody one, so is it that there was a central model trained, that trunk model, and then it was just re-optimized then locally for each client? Is that sort of where you lads say it?
Well, I think at this point I'd probably refer back to the website where they go into the more detail about this splitting of how the trunk, the common trunk works, and then how the optimization happens on the individual servers. But yeah, it's some kind of flavor of that. But the level of technical detail that you need is more eloquently and better put on the website than I can explain here today.
Thank you. So I think another point I would like to have a look at is the questions that perhaps we didn't really talk about today, which are ethics, biases, fairness. I think Martin, at least this morning, mentioned the fact that it's very difficult to distinguish some adversary that would like to pollute the data set with some kind of, let's say, racial bias or, I mean, data that would influence the algorithm in order for it to learn, I mean, bad things, from, I mean, a small community that will have a diverging opinion and that you would like to take into account, or, I mean, some other part of the distribution that you haven't seen before. It's very difficult for that. I think it's somehow related to what we do, I mean, this kind of aspect of personalization and, I mean, how distribution and heterogeneity affects the algorithms, but there are, I mean, much bigger questions about what's the impact of our algorithms on the public and society. So, Mev, perhaps if you could just, I mean, summarize some of the challenges that you face in terms of fairness and ethics, and what the solutions are. I mean, can you say a word on that?
Yeah. So I guess in general, fairness, as I think Jan said earlier, is like it's ambiguous. You know, it's a contested topic. So fairness can mean different things to different people and different companies. So that's one of the reasons why it's so difficult. And also there's very little legislation out there. So it's up to organizations themselves to determine what they think is fair and implement that. So that, I mean, that is a lot of the complexity of it. So you have to decide what's your definition of fairness, then how you're going to quantitatively measure that, how much you're happy for it to diverge from the, you know, be unbalanced, what you do about it, and all of that takes time in organizations from quite senior people and a multidisciplinary group. So that's one of the reasons it's taking a long time. And like I'm actually working at the moment on a project with the Monetary Authority of Singapore that's looking to define a methodology for fairness, ethics, accountability, and transparency for financial services. And like the questions that you keep, and it's with a consortium of FS companies, and the questions that keep getting is, okay, just give us the rule. You know, what is it? Because that's what they want. They just want, if you tell us what the rules are, we can optimize those rules. Whereas it's not, at the moment, it's not as easy as that because there isn't regulation. So I think that's what makes it complicated. I think the interesting thing about this morning and fairness from a federated learning point of view is a lot of the discussions around fairness was talking about fairness for the participants in, like the clients in federated learning, rather than traditionally fairness is about the individuals that the eventual model is applied to. So I think in terms of the first one, what was discussed this morning, the participants, to your point, have a choice. They can participate or not. So that's going to be naturally solved because they won't participate if it's not fair for them. So that's something, and you can see in the research, a number of the pieces of research today were tackling exactly that question. I think the other definition of fairness in terms of being fair to the people who the model is going to be applied to is one that's very easy to miss because oftentimes they don't have a choice. You know, it's just applied for them. So that's the aspect of fairness that I think probably wasn't really touched on today, and probably would be an interesting place to research, because there's a lot of aspects, because you can't see the data. It's hard to do when a model's centrally trained. You check the accuracy on the central model with your data set. In a traditional federated learning setup, usually there isn't a central data set, so it would have to be checked for fairness individually at the client, and each client could have a different definition of fairness for themselves. You know, so it gets very complicated. So I think there's a lot of challenges there from a fairness point of view.
Yes, and do you think, I mean, any of you, do you think that there are some conflicts or overlap between fairness and privacy, and perhaps Aurélien?
Yeah, so I can speak to the maybe more fundamental aspects of this question, because there is some recent research on it. So maybe at the high level, if you take fairness to be kind of, you want a model to have the same kind of performance maybe for subgroups or maybe for the different participants in the federated learning scenario, you can see how there can be tension with privacy, and because privacy probably wants that nobody has too much influence on the result, and maybe fairness, for fairness to be achieved, you might need to kind of give more weight in a way to minorities or people that kind of diverge from the mean or something like that. So there is potentially a tension. There are some impossibility results, like formal impossibility results, between some notions of fairness and differential privacy, but they are very, very restricted. And so I think this is still a very open question. So people have seen in practice some differentially private algorithm like DP-SGD harm fairness. So even the model is potentially without privacy already unfair, but if you add privacy, then it becomes even more unfair. But we know also that if you use different algorithms that also satisfy differential privacy, this effect might be lower. So in my opinion, this is not settled whether there is really an formal incompatibility or trade-off there between privacy and fairness. And of course, it depends also a lot how you define those things. But from a research point of view, it's quite an open question.
Thank you very much. Any comments on that, perhaps? So I think we have a couple of minutes left. I think 5 minutes left, if I'm correct. And I would like to take questions from the audience, if there are some. I cannot.
Whilst the audience thinks of a great question, just to maybe add on fairness, I like the idea that with federated learning, especially to what you were saying, Maeve, about fairness to the end user or the end beneficiary of the inference of the algorithms, that federated learning actually kind of pushes towards a more fair setup, because you're now kind of saying, okay, well, you know, if every algorithm, let's say, that you wanted to use in a medical setting had to be trained using federated learning, you're now forcing an instance in which multiple hospitals have to contribute data, and so in theory, you'd be increasing the heterogeneity of your data. You'd be training on a more diverse population. And now, of course, if you're only picking hospitals from very affluent areas, you might not be very fair from that perspective. But if you could start to say, okay, well, we need federated learning algorithms that are trained on a minimum of 5 different hospitals, and these hospitals need to be in such and such geographies. So it needs to be one in an urban setting, one in a rural setting. You can start to say, okay, well, we're looking for algorithms that have seen that diverse data, and perhaps create a world in which you have these algorithms that are more that are more fair to the end beneficiary, because they've seen a more diverse set of data. And also, it will increase the robustness of your algorithms. You're not overfitting for one particular population. So I think it's a better way to go. It's fair for the end beneficiary, and it's also better for the algorithm itself.
Thank you very much for that. And I think it's a great way to end the day, because it somehow matches some of the ideas that Marco presented this morning on the first talk, trying to reduce variance by sampling in each cluster of data when there is heterogeneity. So we have, I think, closed the loop. And I would like to thank all the participants of the panel again. And also to thank perhaps all the speakers of the day. I think we're going to finish this panel right now. Perhaps is there a concluding words, Mathieu, or otherwise? I think we can just thank again all the speakers of today's sessions for the great talks we had. And obviously all the participants too, both on-site and online, and all the sponsors, so especially Accenture and Okin and the SFDS and Sky that made possible this event. And I think now we can move to the cocktail that is happening in the Zamansky Tower, and we can have a good view there for people on site.